Hi, can you guess the band that I'm referring to here? That's right, it's One Direction. You've got Harry and Zayn and all the rest. I'm a huge fan, can't you tell? Hi, I'm Michael Palmer. Welcome to our lesson on an introduction to graphs and networks. In this lesson today, we're going to review some of the terminology from year 11, stuff like what is a graph, what's a vertex, what's an edge, things like that. We've also going to have a look at directed graphs, which you may or may not have seen already, depending if your teacher showed you. Let's dive in and take a look. Let's review some terminology. Graphs are diagrams that illustrate connections. They're useful for modeling road maps, electrical networks, and so on. They contain vertices and edges. Vertices are colored in dots, or sometimes we call them nodes, and the edges are the lines that connect them. So here we've got some dot points about vertices. So vertex is one of the dots, nodes in the diagram. It can be connected to other vertices by an edge or remain unconnected. A vertex that is not connected to any other is called an isolated vertex. So here in the diagram, this one here, that's the isolated vertex. I want to draw your attention to this intersection of the edges just here. That intersection point, that's not a vertex. Just because the lines cross doesn't mean that there's a vertex there. So important to keep that in mind. It's an easy way to make some mistakes when you're doing some problems. The other dot points we've got about edges here is that edges are the lines in the diagram. They connect the vertices to one another. An edge can also connect a vertex to itself. This is known as a loop. So we've got one loop in the diagram here at A. There it is there. So just look out for loops. The best way to become familiar with the terminology we have to use is to just look at lots and lots of graphs. You'll gain a better and better understanding the more questions you do, the more graphs you try and draw or interpret. Here we've got some different kinds of graphs, so let's go through some definitions. So we've got connected and complete graphs. And so a connected graph allows every vertex to be reached from any other vertex, so long as you move along the edges. The vertices can be reached by any number of steps. This is different to a complete graph, where every vertex has to be connected directly to every other one. On the left here we have a connected graph. You'll notice that this vertex is not connected directly to this one, but we can still reach it by, say, walking through like this. So that's connected. This complete graph is also connected, but we call it complete because if I choose any two vertices, there's always a path directly between them. So you could pick another two and verify that there is an edge connecting those two vertices. We've got disconnected graphs here. So a disconnected graph contains at least one vertex that is not connected to any other vertex. Okay, so here's our disconnected graphs. You can see I've given two examples here. One where we've just got a vertex off by itself, but I want to be clear that there can sort of be two parts to the graph that are disconnected. So here we've got these two guys separated, and notice that the disconnected graph can still have other edges connecting in the other part. The last one we've got is a simple graph. A simple graph does not contain any multiple edges or loops. Okay, so a multiple edge, if I was to draw that in, say on this disconnected graph, these two would have multiple edges if I had more than one edge connecting any two vertices. So I'm going to get rid of that so we don't get confused. So you can see in this simple graph over here, there's no multiple edges and there's no loops in the diagram. More terminology. We're looking at bridges and the degree of vertices. A bridge is an edge that if you remove it, it's going to create a disconnected graph. And the bridges in this graph have been highlighted in red to show you where they are. So if we were to remove either of these edges, then we wouldn't have a connected graph anymore. And so that's what makes them bridges. If, say, we removed like this edge here, we'd still be able to get to those vertices without taking our pen off the page or our pen off the graph. So we'd still be able to, say, walk around this way, or, we could take that longer path to get between those two vertices. So I think that's clear as to what a bridge is. We've got the degrees of vertices. So the degree of vertex is the number of edges that are attached to that particular vertex. However, there is a rule with loops that we need to look at. A loop contributes a value of 2 to the degree of a vertex. The way that I think about this is how many lines can I see coming out of one particular vertex. So let's start with this vertex here. I can see sort of like 5 ways to leave, or you can think of 5 ways to get into that vertex. So the loop sort of connects the vertex to itself. So we count that as 2. And that's just sort of our rule for counting. Every other one we just count once. So we can see this vertex up here, that's got a degree of 4 because there are sort of 4 ways to leave here. We have a rule for the degree sum, and what the degree sum is adding up all the degrees of each vertex. So this rule is that if you want the degree sum, it's 2 times the number of edges. And that should sort of make sense because an edge has to connect to 2 points of the vertex. Every time you count an edge, you count 2 ways to leave a vertex. Not necessarily the same vertex, but that's still two ways every time you make a new edge on the graph. So, I could add one in here if I wanted to. I could put one here, and you can see that I've added a way to leave this vertex here, and I've added a way to leave this vertex there. So hopefully that gives you some intuition as to why that rule must be true. Moving on to planar graphs. What makes a graph a planar graph? It's something that can be drawn in a 2D plane without any of the edges intersecting. Although we can still see a planar graph drawn in that way. It's just sort of like, well, can we make the graph so that there are no intersecting edges? So these graphs here, they demonstrate the difference between edges intersecting and an intersection at a vertex. This here, that's a problem if we want to call this graph planar. We need to be sure that we can sort of stretch that edge or move some vertices so that there's no longer that intersection. So one way to do this is to pull this edge out around to the side, and we're allowed to make that move. And you can see I've sort of prepared that image there. And so we can see this graph is planar. This graph here is planar as well. It's just not immediately obvious. We do need to be able to redraw it so that there aren't any of those crossing of edges. An important part of looking at planar graphs is to look at the concept of faces. In fact, we can't really look at planar graphs without looking at what a face is. We usually draw these graphs in a 2D plane, so it's relatively easy to see what a face is. I've listed 6 faces here. You want to make sure that a face is enclosed by at least 3 vertices. If it's not, we can't count it as a face. Let's have a look. So this one is actually a flattened cube. You can sort of imagine having a cube on the table and sort of pushing it down. And this is the sort of important face to look at here. It's on the outside, or you could imagine it as the bottom of that cube that touches on the table. So when you flatten it, these are the sides here, F2, F3, F4, and F5, and F1's the top, and F6 is sort of that face underneath. You don't have to think about it as a 3-dimensional object being squished. Just remember there's always a face outside of that planar graph. If you're going to assign faces, you have to redraw your planar graph so there's no intersecting edges. This brings us to Euler's rule, which applies to planar graphs. Here it is here. We've got V minus E plus F equals 2. So Euler's rule tells us a relationship between vertices, edges, and faces. And so it turns out if the graph is planar, if you count the vertices, if you count the edges, and you count the faces, and you put them in this formula, you should always get 2. If you don't get 2, then the graph's not planar. Finally, we're going to talk about isomorphic graphs. Graphs that appear to be different may contain the same vertex to edge connections. So they have to have the same structure. The same edges must connect the same vertices in the same way. There are some subtleties around isomorphism depending if the graphs are labelled or unlabelled. In the VCE General Maths subject, we mostly consider isomorphisms of unlabelled graphs. So these two here that I've drawn are isomorphic, and hopefully you can see that I've just moved this edge to point up here, and I've shifted the other one over a little bit. So you can see that the same vertices are connected to the same vertices, and we've got the same number of edges, and those edges are connecting the same vertices. You might like to think in a simpler way, can you redraw the graph so that it looks exactly the same? So you could lay them on top of each other, because if the graphs are unlabelled, you should be able to do that if they're isomorphic. Okay, here's our first worked example. We need to verify Euler's rule for the graph provided. Remember that if we want to verify Euler's rule, we need to be able to count the faces. And to do that, we need to see if we can redraw without these problem intersections. I think we can. So I've got a template here, so I'll show you how we can do that. Okay, so I've got the same picture here, but I've removed these two edges. And what we're going to do is just draw them outside the shape. So this first one here, I'm going to draw that out there. And this one here, I'm going to draw that around the other side. Now we've got a finished graph. It's not beautiful, or as beautiful as what was provided to me, but we can still work out all the things we need to. So I'm just going to make a list here for vertices, faces, and edges. And then we're going to see that we can apply Euler's rule to get 2. Let's count the faces. I think we've got 1, 2, 3, 4, 5, and one outside makes 6. So our faces, we've got 6 faces. If I count the vertices, that's 1, 2, 4, 5, 6, 7 vertices. And the number of edges, easy to count now. I think we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges. And so now I'm going to substitute into the formula V minus E plus F. I'm not going to let it equal 2 yet. I'm just going to find out what this is and hope that I get to 2 when I plug all the numbers in. So let's do that. V minus E plus F. Well, V was 7, E is 11, so minus 11, and F is 6. So let's add 6. And I think 7 minus 11 is negative 4, plus 6 should be 2. So there we go. We've verified Euler's rule as required. Did it. Okay, here's another worked example. We're looking at degrees of vertices here. So for this graph, I need to state the degree of vertex A, B, and C. I need to calculate the degree sum, and I need to identify any bridges. Let's start with part A. So let's find the degree of A, B, and C. So I'm going to look at vertex A first. And remember, if I'm counting the number of sort of paths in or the number of paths out of a vertex, a loop will always count for 2. So there's 1, 2, 3 ways to leave the vertex. So the degree of A, which I might write as deg of A, is equal to 3. Let's do the same thing for B. There's B. And the number of ways I can leave B is 1, 2, 3. So the degree of B is also 3. And looking at C for our final one, there's only one way, and it's right there. So the degree of C is equal to 1. Let's calculate the degree sum. And to do that, we need to work out either the number of edges or we need to work out the degrees of all of those vertices. So what I'm going to do is find the number of edges and multiply it by 2. So the degree sum will be equal to 2 times the number of edges. Okay, we've cleaned up our diagram there, so let's count the edges. That loop is only one edge. It's an edge that connects to the same vertex, so we count it once. And that's different to counting the degree from the vertex. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I've got 12 edges. So my degree sum should be equal to 2 times 12, which is 24. You could verify all the individual degrees of each vertex and then add them up, and you should get that there's 24. So I'll leave that for you to do if you don't believe me about the formula. Last part in C is to identify any bridges. So I'm just going to clean the diagram, and I'm just going to point out where the bridges are. It takes just a little bit of practice to spot them. So I can see one here from B to A. So that's definitely a bridge. If I cut that off, there's no way for me to get from the other part of the graph to vertex A. The other bridges I can see are from C to B. If I remove that edge, there's no way to get to vertex C from the rest of the graph. And finally, I can see from B to D is a bridge, because if I cut that off, then I'll separate C, B, and A from that top sort of kite part of the diagram. So the bridges are AB or BA, whatever you want to call it, CB and BD. Okay, that's the question done. Here's another example where we have to redraw a graph to see if it's planar. This one actually tells us we've got a planar graph. So the question reads, draw the graph provided in planar form. The question sort of hints that it can be done, and we just have to find the way to do it. Truth be told, the way that I wrote this question was to draw a planar graph, and then I just smushed it all up so that it doesn't look like one anymore. So I do know what the answer is here. When you get a question that you haven't written, you might have to play around and draw more than one graph to finally unravel the picture. I'm sort of cheating here, but I'll try and do it maybe in a step and show you bit by bit how you could get from here to the answer. Okay, the first thing that sort of helps is you might want to identify all the intersections of the edges that are preventing it being a planar graph. They're here. And so you might notice that along the line AC, so along this path here, we've actually got 2 intersections there, and along BG, we've got 3. So those are our biggest problems, and what we can do is we can push BG below, and we can bring the vertex A, we can sort of swing it up and around. So I'll try and draw that to show you what I mean. Okay, so I'm just going to draw this graph again, B, D, E, G, and then I'm going to swing that A up the top. So I'm going to put it here. So I've just moved that sort of triangle, I've sort of flipped that up. And then you can see there's a connection from A to C. So I'm going to complete this triangle here. So there's C. We've got most of our connections there, but C still needs to connect to A, and we can just draw that across the top there. And so you'll notice that's removed 2 of the intersections we had before. We can also see that we've got a triangle down below here, so we need to draw that in. So I'm going to put F in. Okay, there's F. And the only connection I think we have left to make is from B to G. And so I could wrap that around the top or the bottom, it doesn't matter. So I'm just going to put it in here. And I think there I've done it, and we've actually provided a nice looking one. It's not always easy to spot. I mean, it's easy because I can sort of see the answer on the screen. I can show you slowly how we could generate it, but you might make a move and that's the wrong move. And my suggestion would be, if you're getting really lost down a rabbit hole, is to just start again, a different sort of starting move. If you think about it, there's only 1, 2, 3, 4, 5, 6, 7 vertices that you could choose to start from. Or if you're going to start with moving an edge, there's about 10. And So that actually is a finite amount of things you could try. And if you, try it again and again and again with, 10 different edges and you still weren't finding it, then maybe you might like to ask for some help. But don't give up if you fail the first time. All right, before we wrap up, let's have a look at directed graphs. So directed graphs, or also known as digraphs, are formed when we restrict each edge to have only one direction. This direction is indicated by the arrowhead. So we can see that this edge flows from this node to this one. We can see we can have a loop with a direction, and that's fine too. Sometimes the arrowhead might be drawn up close to the node, and that's fine, just so long as you know which way it's going. Here's a summary of the things we talked about today. We've got some formulas there that we used, the degree sum and Euler's rule, and we've got a nice picture there of how to work out the degree sum. Coming up next, we're looking at adjacency matrices. I'll see you there. You almost certainly saw graphs and networks when you're in year 11, and you might have made the connection that your social network can actually be stored as a big graph. And it is. Somewhere on social network, if you've got an account and you've got connections or friends on that account, then those connections are probably stored in the computer's brain somewhere about who exactly you are friends with. And having this graph stored, maybe as a matrix, maybe as a program graph, allows those social media networks to recommend new friends to you. So if you know you've been recommended a friend on Facebook or something, then the way that it's made that connection, that recommendation to you, is by evaluating your network and other people's networks and seeing where you have commonalities. So let's dive in and have a look at networks. Hi, today let's dive in and see how matrices and graphs and networks are connected. Today we're looking at adjacency matrices and adjacency matrices for directed graphs. These are pretty much the same idea, so let's jump in and figure it out. Adjacency matrices. I've got some points here about what they are, maybe what they're not, and let's dive in and have a look and see if we can make sense of all this. So the first point I've got here is an adjacency matrix is a square matrix used to represent a graph. So why should it always be square? Well, if we've got some vertices A, B, C, D, E, and so on, what the adjacency matrix does is show the connections between those in the matrix form. So if you've got 5 vertices, say, then you need to be able to say which connections are formed, right? So we need A, B, C, D, E. We need a row for every vertex. But we also need to say, is it connected to those other vertices? So we need another 5 columns to show all those connections. So here we've got a 2x2 matrix representing a graph with 2 vertices. So these two here are connected. This is the adjacency matrix representing that graph there. So the next point I've got is the number of vertices in a graph will determine the number of rows and columns in the matrix. So we just sort of talked about there. We've got 2 vertices, A and B, and so we need 2 rows and 2 columns. The third point I've got here is the value of an entry or element, AIJ, will represent the number of edges connecting the vertex in row I and the vertex in column J. So what does that mean? Here, this one is representing the connection between the first row and the second column. So the label here is A in the first row and B in the second column. So that position is representing those connections between A and B here. So that one refers to that edge there in AB. This notation AIJ, no doubt you saw earlier in a previous chapter about matrices, or if you've done it in a different order, I think you probably saw it in year 11. So I'm not going to talk too much about that. The values in the elements of the leading diagonal represent the loops present in the graph. This makes sense from our row and column entries because things along the diagonal connect A to itself. So you can see A is connected to itself here, first row, first column, and second row, second column is the second entry in the diagonal, and that's connecting B to itself there. So in this graph, we can see that I've got A connected to itself, and that one is this one here, and this edge, B to B, is represented here. So a good way to check if a graph has loops, if you've got the adjacency matrix, is to just look down the diagonal. If they're all zeros, no loops. If you can spot, a number there, it's telling you the number of loops from that vertex to itself. The last thing we've got here is I've drawn another graph just so I didn't want you to think that adjacency matrices can only have ones and zeros in them. So I wanted to put some other number in there. So my graph here, I've got A and B, and we can see that there's 1, 2, 3 edges connecting A and B. In both of these positions here, we've got a 3. These 3s are sort of telling us the same thing, just sort of in a different order. So this first one says, how is A connected to B? And this position here says, how is B connected to A? And that's really the same question. So what you'll find is that an adjacency matrix is symmetrical about that diagonal. The information in the lower triangle is usually the same as the information in the top triangle. This does change though when we have directed graphs. So we'll look at that in a bit. Okay, we've got a worked example. I'm supposed to create an adjacency matrix for the graph shown. So we're going to do that. First thing I'm going to do is count the vertices. I've got A, B, C, D, E, so that's 5. I'm going to need a 5 by 5 matrix. I'm going to draw it nice and big here. For Edrolo, we're putting our row labels on the right, but you could put them on the left. That's okay, that doesn't really matter. I usually see them on the left in the stuff that I read, but whatever, it doesn't matter so long as we understand what the matrix is telling us. We could even swap the order of things. We could look column first, then row. So long as we communicate to our reader what we're doing, we should be fine. So we've got A, B, C, D, E, A, B, C, D, E from the rows and the columns. First thing I can see, E is not connected to anything. So if there's no connections to E, I can just put zeros in every position. I'm going to do that because it's going to help me line up my matrix so that it looks nice. And maybe I'll go sequentially so you can see how I can fill in each position one at a time. So if I want to find this, say the element in A11, so the first row, the first column, that's connections between A and itself. And so I look at A over here, and I can see it's connected to B and C, but it's not connected to itself. So there's no loop, I'll put a 0. The next one, let's do A12. Okay, well, A12 is this position, the first row and the second column. So is A connected to B? I can see that it is, and it's connected once. So I'm going to put a 1, and then I move to the next one. I've got to do A13, row 1, column 3. So I've got row 1, is A connected to? Row 3 has C in it, so is A connected to C? And I can see it is just here. So I'm going to put a 1 there. Last one I'm going to do, sort of in this fashion, I've got to do A14, so row 1, column 4. So is A connected to D? I can see there's no edge connecting A and D, so I'll put a 0. We can go a bit faster than this though. So if I just look at the second row, I'm looking, well, what's B connected to? I can see that B is connected to itself via a loop, and it's connected to A and C. So I'm just going to fill that in across the rows. So is B connected to A? Yes, it is. Put a 1. Is it connected to B? Yes, it is. Put a 1. Is it connected to C? Yes, it is. Put a 1. And it's not connected to D, so I put a 0. I'm going to use another trick here, just so you see lots of ways to do it. You could keep going like this and fill out the matrix, but I know that B is the only loop present. So down the diagonal, I should only have a 1 in that BB, or position 2, 2. So I'm going to put zeros everywhere else. C is not connected to itself, and neither is D. And what that shows me is in that upper triangle, I've only got one thing left to place. That position is going to be C and D connected, and I can see that it is, so I'm going to put a 1 there. Now what I know is that this adjacency matrix will be symmetrical about that diagonal. And so I don't even need to think anymore. I can just sort of like copy those values in. I imagine them reflecting across that diagonal line. You can use this trick too, but make sure you practice. Don't do it for the first time on your exam or something. So I know that A is connected to B and C. So these ones here, they're going to appear in that column. So that row going to be same as that column. And then looking sort of across here, I can see that there's going to be a 1 there. And I can see that there's going to be a 1 there to make it symmetrical and a 0 there. I've just used the symmetry there. I haven't actually checked every value, but I'm pretty confident we'll be right. Have we got it right? Oh, no, we haven't. We made a mistake. That's okay. Let's fix it. Where do we make the mistake? It's just here because I didn't reflect properly. There's a 0. So that's okay. That method will work. You notice that the mistake happened, but that's okay. You can see that if we want to get it right, we can be really, really careful. Let's move on. Okay, so it's important to be able to construct an adjacency matrix from a graph and make the graph from the adjacency matrix. So here we've got a 3 by 3 graph. I'm going to put in 3 dots. Now we've got a nice answer prepared. For now, I'm just going to make all the connections, and then we'll show you the nice example, and we'll see that they look a bit different, and that's okay. Your graph might not look like your partner's while you're working, but so long as the edge to vertex connections are still the same, you've both got the right answer. First, I'm going to look for loops. That's what I want to do. I can see that there's 2 loops at A, there's 1 loop at B, and there's 1 loop at C. So I'm going to draw them in. 2 loops at A, 1 loop at B, and 1 loop at C. Then I'm going to just look at the top right half. You could go through and check every one, but I'm just going to look at top half. You could look at the bottom half. I can see there's 2 connections from A to B. So there they are there. I can see there's 3 connections between A and C. So let's make them 1, 2, 3. And there's 1 connection between B and C. That's it. Let's look at our nice version, see if it's the same. Pretty similar. You could have chosen to put A, B, and C anywhere, and that's fine, right? So long as you've got the same edge to vertex construction. All good. Make sure you are really clear that this graph is connected to the matrix, like you can go back and check. I guess one thing to avoid was make sure you don't add the edges twice. You know, if you're looking at all the edges and you're just sort of not really thinking, you might have added, 4 total if you did that step twice. So just make sure that you're understanding what the numbers mean and that they're counting the connections between the vertices and the edges. All right, let's look at adjacency matrices for directed graphs. These are pretty similar to the undirected versions we've been looking at before, just a slight difference here that the edge has a direction. So I've got two things here for our key takeaway. An adjacency matrix for a directed graph is constructed in much the same way as for an undirected graph. Each edge will contribute a value of 1 in the corresponding AIJ position, but not the AJI position. This means the adjacency matrix will no longer be symmetrical about the diagonal. So here's an example. I've got a directed graph here and its associated adjacency matrix. So I can see that the edge is going from A to B. And so if I look from A to B, I put a 1 here. You might wonder, why not look this way from column to row? So we've got a 0 here. So how do you know, in other words, which way it goes? Well, I'm telling you that I'll be making matrices that go row first and then column second. We could do it the other way around, but we need to communicate that to whoever's reading our graphs. I think it's most common to see things going row first and column second. Almost all the work I've done with matrices, I always think row first for what I'm doing. And if there's something that goes column first, that's sort of an abnormality that I come across. All the ones you see me make, so all the questions that I'll give you, we'll think about the matrices row first and then column second. Okay, here's a worked example. We're going to construct an adjacency matrix for the directed graph below. I've got a nice version, but we're going to draw one first. Just do it bit by bit to show you how to do it. So I've got 4 vertices, so A, B, C, D. And I'm going to put the same across the top. Okay, and I'm just going to look at my connections. So I can see I've got a loop in that bottom diagonal, so I'm just going to look out for that. Let's start with this first row. Let's look at what A is connected to. It looks like it's connected to B and D. So I'm going to put 1s in those columns. Okay, looking at B on the diagram, looking from here, I can see B points to C, but nothing else. So I'm going to put 0s everywhere but C, but column C. All right, now looking at row C, I can see that C is pointing to A and to D. So I'll put 1s in those columns. So it is connected to A, it is connected to D, but not B and C. And finally, D is pointing to nothing but itself. So that should be 0, 0, 0, 1. Just the 1 in that position there indicates our loop because it's on the diagonal. I think we've got a nice version here, so let's check it's the same. And that's looking pretty good to me. I think we did it. All right, we've got a mega question activity to do. The network below shows the pathway between 5 buildings, J, K, L, M, and N. And we've got a picture there. The adjacency matrix for this network is formed. The number of zeros in the matrix is... So we've got some options there to choose. We could guess, but we don't have to. So we're going to try and draw first a graph. So this looks very much like a graph, but our graphs don't usually join up like roads do. And so we're going to make a graph that sort of works to model this situation. And then from that graph, we're going to make the adjacency matrix. So to do that, I'm going to cheat a little bit and look ahead because I would usually take more than one go to get this right. So I've got my points and I spread them out sort of like they are in the picture. So we've got J, L, N, and then M's over here and K's over here. So now we're going to count the paths from one vertex to another to try and get all these edges correct. So if I look at J to K on our original diagram, to get there, there's a few ways I can go. I can go this way, and that's 1, and I can also go this way. Down through there, and that's 2 paths I can take from J to K. So because there's 2 different ways I can get there, I'm going to put in 2 edges, J to K. Let's clean up the diagram, and now let's look between K and L. To get from K to L, I can take this path, or I can go all the way around and take that path there. So there's 2 paths from K to L. It's really easy to miss a path here. So we do need to be very careful. And actually, when I do this type of problem, I always look out for loops. So can I get back to the same vertex along a path? And it looks like there's a loop at K. So I can go all the way along the road like this and come back to K. And so I'm going to add that loop in there. That's looking good so far. Now let's pick some different vertices. Let's try and figure out the connections between L and N, perhaps. So it looks like there's just 1 there. I don't think I can get there without passing through some other vertex. So there's just 1 connection between L and N. And that's sort of how you know how many paths you have. Okay, let's see. Can we go from L to J? Can't go that way because we'll hit N, but we can go this way. And I don't actually think there's any other way to go there. So we'll have 1 connection from J to L. And that makes me want to find the connection from J to N. So I can sort of just see there's that one. And I can tell following the path there's no other without hitting a vertex. So we've just got 1 path from J to N there. We've got to connect M to all the other vertices now. So let's have a look, clean up our diagram. Let's look from M. We can get directly to L and K. I'm going to put those in there. I think that's it. They're the only ones I can connect to directly. And I can see that I can't get from M to N directly. So that's my final graph. And so now I need to make an adjacency matrix. So that's only halfway done. So let's make our adjacency matrix. You can actually make it in any order you like, but I'm going to do J, K, L, M, N in alphabetical order. Okay, so looking at J, to get to J doesn't connect to itself. It connects to K twice. It connects to L once, to M no times, to N once. I'm going to connect K to everything else. So let's look at K. So looking from K, K is connected to J twice, itself once. K is connected to L twice. It's connected to M once, and N no times. Easy to make a mistake here. Let's keep going. Make sure we get it right. From L, can we connect L to N? Yes, we can, just once. M, just once. L is connected to J once, connected to K twice, and not connected to itself. Okay, we're getting there now. Let's look at our connections for M. So M is connected to L and K, so we'll fill that in, and N is connected to L and J. I think that's our adjacency matrix, and we get asked how many zeros there are. So I'm going to count them up. 1, 2, 3 in that row, 3 in that row, 1 in that row, 1 in that row, and 2 in the top row. Makes a total of 3, 6, total of 10. And so the answer is C. But what I can see here is we've got a percentage breakdown of how many people got it right. And so we can see about 33% of the cohort chose C. So not very many people finding that easy. So there's our final graph there. There's a nice version of our matrix in our graph. Looks like we got it right, which is good. I think taking the time to work out getting from this picture to this graph is a certain skill. So you want to practice that every time it comes up. Okay, here's a summary of some of the things we talked about today with a few examples of graphs and their associated adjacency matrices. Coming up next, we've got exploring and traveling problems. We've got some notes here if you'd like to take them. See you next time. If you're ever lucky enough to spend some time in London, you'll have to navigate the network of the Underground. Look out, it gets really hot in summer, but it's totally worth checking out that city. Welcome to Exploring and Traveling Problems Part 1. Today we're looking at walks, trails and paths, and our next KU is circuits and cycles. Let's go over these definitions again because you've probably seen them in Year 11. Walks, trails and paths are all descriptions of a sequence of connections of movements on a graph. Each term has a slightly different meaning, so we've got some definitions here. We've got a walk is a series of edges where repetitions are allowed. This goes through any number of vertices. Pretty much every movement through a network is a walk. A trail, however, is a walk where no edges are repeated. However, they may pass through the same vertex more than once. Degree of complexity out from this is a path, which is a walk where no edges or vertices are repeated. In a trail, we don't mind if we repeat like a vertex, but in a path, we can't repeat edges or vertices. So you might think about it in that sort of ranking. A walk is a way for us to move along a graph using the edges to go from vertex to vertex. On a walk, we're allowed to repeat edges and vertices as often as we like. When there's no ambiguity, we can represent a walk with a sequence of labeled vertices. What am I talking about? Here's a list of vertices that our walk is going across. So this one goes B, A, E, D, A, B, A. So let's have a look at that. Let's start at B and let's go to A and then we'll go to E, D, A, B, A. So you can see we visited the same vertex more than once. We visited A few times there and we walked along that AB edge a few times. That's a walk. The repetitions are allowed in a walk. If say we had, a connection A to B and we were using this sort of vertex notation, if there are multiple edges on A to B, it can be unclear which edge we're walking along. So just keep an eye out for that. There's another example here. We've got a walk MON, MM, PQ. Here, that double M is referring to a loop. So let's do that walk and see what it looks like. Start at M, go to O, then N, go back to M again. The only way to do that in one step is to take the loop and then go to P and then to Q. Okay, so that's what our walk looks like. You'll notice that looking at the final product, it's not really clear where we start because we've got this cycle happening here. So sometimes we need this description to be clear about what the walk looks like. A trail is a walk where the edges are distinct. That is, the edges may not be repeated on the walk. Vertices are allowed to be repeated though. We've got the same graphs here. Let's find a trail on each of these graphs. So here I've got one that's BAE, DAC. So let's look at that. Start at B, we'll go to A, we'll go to E, then to D, back to A, and we'll finish at C. So notice that we didn't repeat any edges along the way, but we did repeat that vertex A, but that's okay. This is still a trail. Here's another one. We've got MON, MMPQ, which I think might be the same as before, but let's follow it along again. M to O to N to M to M to P to Q. Okay, and you might think, well, that's the same as before. How can it be a walk and a trail? That sequence of like vertex to vertex traveling satisfies both definitions. It is a walk and it is also a trail. So we're going to give it, if I had to choose, I'd call it a trail because that most aptly describes that set of edges or that edge traversal. It is a trail. It's also a walk. And so is the other one. That's actually a walk as well. Right? Pretty much everything's a walk, but they also satisfy that definition of trail. A path is a trail where no vertices or edges are repeated. So that edges is sort of inherent. So you can sort of think of these definitions as cascading. So it sort of becomes harder and harder to become. A walk's easy, a trail's a little bit harder to achieve, and a path's a little bit harder than that to achieve because you've got more conditions you have to satisfy. Notice that repeating an edge will require that a vertex is repeated. So a path has no repeated vertices or edges. That's saying that in some cases, if you want to come back to the vertex, you have to come along the same path. We've got BACE here. That's apparently a path. Let's see what it looks like. We start at B again. We'll go to A, we'll go to C, and we'll go to E. Okay, this is a path. It's also a trail because we didn't repeat any edges, but because we didn't repeat any vertices, that's sort of the best definition we can give it. I'd say that's the most apt description. So I'm going to call that a path. Okay, the next one has got Cupimon, mayonnaise Digimon, I guess. MONPQR. Let's have a look at that. Start at Q, go to P, go to M, go to O, and then N. Okay, and so we can see there that there's no repeated vertices, no repeated edges, so that is a path. Excellent. Okay, let's do a worked example. This one reads, choose the terms that apply to each diagram. More than one may be chosen for each. So the words I get to choose from are walk, trail, and path, and I can choose more than one. I'm going to try and indicate what I think the best descriptor is of that particular sequence of edges. Let's look at the first one on the left here. We've got A, B, C, D, E, F, D, B, and I'm going to try and draw one continuous line along that walk, trail, or path. Let's have a look. So we go from A to B to C to D, and we've got these arrows here to help us. E, F, D, B. Okay, so that's sort of the way that we're working along, and I can see that I'm repeating a vertex B, and that's okay. So it can't be a path, but I'm not repeating any edges. So I think we can say this is a trail, and that's probably the best description of this sequence, but it is also a walk. Pretty much everything's a walk. Okay, next one. We've got C, D, E, F, D, C, B, F, A. So let's start at C, and let's use those blue arrows to help us walk along. C, D, E, F, D, and then C, then B, F, A. So I can see I'm repeating that vertex F, and looks like I repeated this edge here at C, D. So we've got a repeated edge, which means that it can't be a trail, and that means it can't be a path either. So this is just a walk. Now, last one, we've got D, A, B, C, E, H, G, F. So let's start at D and go to A, and let's follow that path around. Sort of the blues sort of helping me do that there. D, A, B, C, E, H, G, F. I can see that I haven't got any repeated vertices and I haven't got any repeated edges. So this can be called a path, and that's probably the best descriptor, but all paths are trails and all trails are walks. So you can think about those definitions sort of cascading down there. If we've got no repeated vertices and edges, then it's a path. If we can have repeated vertices in a trail, and we can repeat edges and vertices in a walk, right? So path's sort of the hardest one to achieve there. Our key takeaway here is that a circuit is a trail in which the beginning vertex is the same as the end vertex, and where no edge is repeated. Okay, so that no edge repeated, that's contained in it being a trail. A circuit can repeat a vertex other than the start-finish vertex. Okay, so if you're going around and you happen to visit the same vertex twice, but you manage not to repeat an edge, that still can be a circuit. All right, let's annotate some circuits. One simple one would be A, B, C, A. That works. We could say that that's a circuit. And the next one, which is a little bit more complicated, let's do circuit 2. We're going to go A, B, C, M, D, A. So we can see we're starting and finishing at the same place there. So that can be considered a circuit. We're also going to look at another one here. I'm going to write it out. B, A, M, D, A, C, B. Let's look at this one. So B to A to M to D to A. So notice we're visiting that same vertex A. and then we go C, B. So as we start and finish the same place, we did make a repetition, but it was just a vertex. So that can still be a circuit. Let's try a worked example. We're going to apply the terms walk, trail, path, circuit, and cycle to the routes provided below for the graph shown. We can assign more than one word to each route, and at the end, I might choose the thing that I think is the best description of that. Here, this gets a bit tricky because the definitions cascade. So things like a circuit is a trail. It's just a special trail that sort of finishes and starts at the same point. So we're going to see that we come across that here. So let's jump in and have a go. I'm going to annotate all the trails. So we're going to start here at A, B, C, D, E, C, A. So let's draw that one here. A, B, C, D, E, C, A. So I can see I'm repeating this vertex at C, and that's going to stop it being a cycle or a path. Those things both need that we don't repeat a vertex or an edge. So here, this is a walk. It starts and finishes at the same point. So that's going to mean that it's a circuit. So it's a circuit, a walk, and a trail, because circuits are trails, just special ones that end and start at the same point. So here, actually, I've got walk and circuit, so I've overlooked that this should also be a trail. Just a heads up, I think circuit here is the best definition, right? If we're starting and ending at the same point, we should be using circuit or cycle to describe that particular traversal across the graph. Looks like this one's going to be walk, circuit, and cycle. That's right. Let's have a look now and see why that should be. So we go from A to B to D to E to C to A. So we can see that that's a closed sort of walk there. So we're ending and starting at A. So that's going to be a circuit or a cycle. So all circuits are cycles. So the condition here that's different is that a cycle can't repeat a vertex or an edge, whereas a circuit may repeat a vertex. The best word here, I think, is cycle. That's what I'd choose if I had to choose one. But technically, it does fit the definition of circuit and walk. And I guess trail and path while you're at it. BDC turns out to be a walk, trail, and a path. So let's have a look. B to D to C. So this is pretty clearly a path because we don't repeat any edges or vertices. That means that sort of cascading down, it must be a trail because we don't repeat edges and vertices, and is a walk because pretty much everything's a walk. Next one. Turns out to be a walk, trail, a path, a circuit, and a cycle. Okay, this is all of them together. So let's have a look. Start at B, go to D, go to C, back to B, and that's where we finish. So starting and finishing at the same point, and we've got no repetitions of edges and vertices. That's our top one there. That's a cycle. It also technically fits all those other definitions. If you look closely at those definitions, you'll see that it doesn't break any of them. Let's do this next one ourselves. B, C, D, E, C, D, B. Okay, let's have a look. We go from B to C to D to E, back to C, notice we're repeating there, back to D, and then to B. Here, I can see that I'm finishing and starting at the same point, but I am repeating vertices and edges. So this is only going to be categorized as a walk. Last one. This one looks like it's a walk and a trail. So let's have a look. We go from C, I'm going to finish at A. So we go C, B, D, E, C, A. This is going to be a walk because everything's a walk, but why is it a trail? Well, we are repeating that vertex C, but that's okay. That's allowed in a trail. That's why. So we've made some path where no edges are repeated, but it's okay to repeat that vertex. It's not a circuit or a cycle because we don't start and finish at the same point. So these are the right words to use, I think. All right, now I said I'd choose the best one. So I think trail's the best one here, walk's the best one here, cycle's the best one here, path's the best one here, cycle's the best one there, and circuit is the best one there. So I've assigned more than one word because I think they fit the definitions, but I have also chosen the best one that I can. Here's a worked example. It says, find the longest circuit possible for the graph shown. How many edges were traversed? Now, there's going to be more than one longest circuit here, but any one that's sort of got the most amount of edges it can have is fine. And so the one that I've got here is going to start at A, but you could start anywhere, I think, and go A, B, C, D, E, C, A. And if you can find one longer than that, I'd want to hear about it. Okay, so I think that's 1, 2, 3, 4, 5, 6 edges traversed. And so I've got a sample answer here with a note that there's other solutions. Okay, so you could probably start somewhere else and do the same pattern, and that would all work. But if you can find one longer, I do want to hear about it because I couldn't. Cycles. Our key takeaway here is that a cycle is a path in which the beginning vertex is the same as the end vertex, and no vertex or edge is repeated. The starting vertex may be repeated to complete the cycle. So we've done some questions before without me explaining what a cycle was, and that's because you actually encountered them in year 11. So I'm hoping that that was sticking around and it was okay to ask that in the questions before. Let's annotate some cycles. So here in the hexagon, I'm going to annotate A, B, C, D, E, F, A. I think going around like that, that's definitely a cycle. Notice that we don't repeat any vertices or any edges, and we start and finish in the same place. Here's another one. I'm going to annotate the cycle M, E, D, A, B, C, M. So let's start at M for middle and go E, D, A, and then B, C, M. Okay, so that's a cycle 2. That brings us to our summary, where I left a definition of all those things there if you'd like to add them to your bound reference. We've also got a list of walks, trails, paths, circuits, cycles, so you can draw that diagram out yourself, maybe a few times, and maybe highlight over the paths to help you remember which one's which. What's coming next, you've got Eulerian trails and Eulerian circuits, and there's some key terms there. Make sure you do know those definitions. It's important. If I was to give you some advice, I think the best way to do this would be to try and draw a graph and then find one of each of these within that graph. Trying to make this up yourself is going to help you remember it. All right, let's go to the next lesson. All right, today's hook is about Leonhard Euler. That's Euler, not Euler. Don't let your teacher say Euler. Don't let your classmates say Euler. It's Euler. This guy is like the best one ever. He's referred to by other mathematicians as the master of us all. I think he was pretty clever. And, you can tell because look at that super cool hat he's got there. People say if you want to learn mathematics, you should read Euler. Look, I'm not good enough yet to read his papers, I don't think. But if we have a look at his eye there in the picture, you can see it's sort of closed. And Euler actually went blind later in life, but he was sort of so clever. He had photographic memory, and he could sort of just speak maths to his scribes. So he could sort of see it all up here and ask them to write it down for him. So he kept writing papers even after he went blind. I think the story goes that it didn't even slow him down. He actually kept publishing papers faster than ever before. So, he's a pretty cool guy. Luckily, we've got this classic painting of him to see what he looked like. And check out that, again, glorious hat. Welcome to Exploring and Traveling Problems Part 2. Key points today are looking at Eulerian trails, Eulerian circuits, and generating graphs from maps. That last KU there, that's sort of referring to this common kind of VCAR question. We sort of saw, making a road diagram into a network earlier on. It's sort of to do with that. The other two, I'm going to be referring to these as Eulerian trails and Eulerian circuits because that's how I think it should be pronounced. However, your teacher or other people might say Eulerian trails or Eulerian circuits, and I think that's okay and that some people refer to them that way. I'm not actually sure. I tried really hard to figure out what the right pronunciation was. If there's a mathematician in the audience, I'd love to hear from you and know the right answer. Okay, Eulerian trails. An Eulerian trail is a trail that follows every edge exactly once. The conditions required for an Eulerian trail to be present are that the graph is connected and the graph has exactly 2 vertices of odd degree. All other vertices need to have an even degree. Additionally, the Eulerian trail will always start and finish at the vertices with odd degree. A lot to take in all at once. I think the main thing here is you're trying to get across every edge without repeating an edge. So let's have a look here and see if we can do it. I've got a walk listed here, B, A, F, E, D, C, B, G, E. So let's follow that one and see what it does. Let's start at B and go to A, and then go to F, and then to E, to D, to C, to B, to G, to E. Notice that I've traversed every edge there without repeating an edge. I did repeat a vertex, but that's okay because it's a trail and trails can repeat vertices. So this is an Eulerian trail. It satisfies these conditions. Fantastic. One thing about the degrees here. If we go across and we count the degrees of the vertices, I'm going to put that down here. There's 2 edges coming out of that vertex. There's 2 coming out of F, 3 coming out of E, 2 coming out of D, 2 coming out of C, and 3 coming out of B. Notice that exactly 2 of the vertices have an odd degree. That's 3. And that's important. And when you're looking for an Eulerian trail, it has to be that it starts and finishes at those vertices. Notice that we started at B and finished at E. That's not a coincidence. So when you're trying to find one in the graph, it's a good problem-solving strategy to count the degrees first. If you've got 2 edges with odd degree, good chance that you're going to be able to find an Eulerian trail. Here's a worked example. Does an Eulerian trail exist for the below graph? If so, state the trail. So first thing, I've got to figure out if an Eulerian trail exists. So I'm going to count all the degrees. Let's do that now quickly. There's the degrees of the vertices, and we can see that we've got 2 odd ones. We've got B and A. So what I think is that my Eulerian trail is going to have to start at A or start at B and end at the other vertex. Let's do it. I'm going to state the trail. It says state the trail, but there are more answers, okay? So my one I'm going to say is, look, I've got the answer here, so I'm going to tell you what it is. It's A, B, C, D, E, C, F, E, A, B. So that's the answer. But when I was finding this, you would actually probably draw over the graph first and then state the sequence of vertices at the end. So let's follow that along, A to B, and then we go through C, and we're going to go D, E, C, F, E, A, and then all the way around to B. Okay, there it is. There's an Eulerian trail. Okay, another question. Does an Eulerian trail exist for the graph below? If so, state the trail. Okay, in this case, I think it probably doesn't work out, and we're going to show why. So let's count the vertice degrees. So let's find what they are. There they are. I've got 4 vertices with an odd degree and 1 with an even degree. So I know that for an Eulerian graph to exist, I need exactly 2 vertices with odd degree. And so no Eulerian trail is possible. You could try and find one, but we'd probably fail. Let's try and fail anyway, because that's fun. So let's start at A, and we're going to try and go across every edge exactly once without repeating edges. So I'm going to go A, I'm going to go to B, to C. Okay, going well. And then I sort of run out of options if I go to E. I can't go back to C because then I can't leave, right? There's nowhere to go. So, okay, I can't do that. Failing. Let's go to A. That's allowed. Okay, and then I'll go to E. But then I've got too many options. If I go to B, I'll get stuck. If I go to D, I'll get stuck. If I go to C, I'll get stuck. So I couldn't figure it out. You could keep trying things, and I think you'd keep failing. You wouldn't be able to do it. Some Eulerian trails just won't exist for some graphs. So let's take them away. Can't be done. On to Eulerian circuits. So an Eulerian circuit is an Eulerian trail that starts and finishes at the same vertex. So the conditions required for one to be present is that the graph is connected and all vertices have an even degree. We've got one here, and we've got the walk listed, A, B, C, D, A, B, C, D, A. But that alone isn't so clear. So I'm going to show you what I mean by that. So I'm going to start at A. And what I'm going to do is I'm going to go around the inside first, A, B, C, D, A. Visit every edge. Repeat that vertex A, but that's okay for an Eulerian circuit. And I'll go around outside now, A to B to C to D back to A. Okay, now you could go outside first, then inside, or you might even find a different way to do it. That's okay, but we did it. We found an Eulerian circuit, so that's one there. You might think about why we need all the vertices to have an even degree. And I think that's because to start and finish at the same place, I've got to come in and I've got to leave as well, right? So if I've got an even degree, I've just drawn a vertex here. If you leave, you can come back. If you leave again, then you can come back again from some other different way, right? So sort of thinking about graphs in general can get tricky. But maybe think about, as you progress along, why was the Eulerian circuit possible? Why did it matter to have an even degree for all of your vertices? Whereas for the trail, we needed 2 to be odd. Here's a worked example. Is an Eulerian circuit possible for the graph below? If so, state the circuit. I've got some graph there. Looks like a pentagon with some other edges stuck on the edges there. So let's see. Well, is it possible we can do our degree check? So I'm just going to check all the degrees there. So I think A's got 4. 4 for B, 4 for C, 4 for D, and 1, 2, 3, 4 for E. Yep, so they're all even, so it should be possible. And if so, it says state the circuit. Well, there could be more than one, not sure, but the one that I've found goes like this: A, E, D, C, B, A, D, E, B, C, A. Okay, so we're going to start at A, and we're going to go A, E, D, C, B, A. So I've covered all those edges around the outside of the pentagon. And then I'm going to go D to E. Yep. Across to B. And then to C. And then finally back to A. Awesome. Okay, so it looks like we can do an Eulerian circuit for that one there. On to our last KU, generating graphs from maps. A commonly assessed skill with VCAR papers is to convert a map to a graph. So we have this picture here that's not a perfect network, and maybe get it into a matrix form or get it into a network graph form. When creating a graph from any source, a useful question to ask oneself is, how many different ways are there to get from one vertex to another without passing through any other vertices? You sort of want to ask yourself the question, how many ways to get from P to Q, and then from P to R, and then from P to S, and then P to T, and then go to a new vertex and ask all those questions again. If you do that and you're methodical, then you will get it right. However, full discretion here. I took this from a VCAR paper, and the first time I tried to do it myself, I made a mistake. So I know that I'm really prone to errors in this particular area because I tend to rush. For me, this is something that I'd slow down on. And if I was, in an exam condition nowadays, I'd be trying to leave some time for this to make sure that I got it right. So let's do it. I've actually got the finished one here, and we're just going to go through a few points and sort of look how we could do that. We might not go through it all, but let's start at P. And maybe let's look at all the connections coming out of P. So we'll go P to Q, P to R, P to S, P to T, and see how much of the graph we've covered at that point. Starting at P, it looks like there's a loop there. So where's that loop? It's here. There's a route going from P back to itself. So let's color that in. We've done the loop from P to P. Now let's look P to Q. Apparently there's 3 paths. 1, 2, 3. So let's see if we can spot them. P to Q, there's a direct one there. We can also go this way from P to Q, or around the long way before we hit that road there. So that's the 3 paths from P to Q, 3 different ways, 3 different road paths of getting there, right? We've done P to Q, we've done P to itself. Let's do P to S. How many ways from P to S? Well, there's this direct path here, or we could go around and then join up to that road. So that's a long way. So that's 2 from P to S. Now let's do P to T. Can we get from P to T? I think we can just around the outside here, but also taking this a long way. So there's 2, and we've got 2 on our diagram here. This is a lot harder if you don't have, the final graph. That task can be hard. Arranging everything can sort of be a bit tricky. We've got P to R left to do. Well, it looks like P and R aren't connected. If we try to get to R, we hit a vertex, so that doesn't count. We hit Q, that doesn't count. We hit Q again this way. I can't really find a way to get there. I guess also worth noting here, you've got to be doing that in your mind. You can't be drawing all over your diagram because otherwise it'll get too confusing. So hard for lots of reasons here. Anyway, so we can't connect P to R and we don't see that in our graph, so that's okay. And I think we've looked at P to P, Q, R, S, and T. So once we've done that, that's sort of like a fifth of the way there. So now we've got to go to Q. So if we move across the Q and we think, okay, can we get from Q to R? Well, yes, we can here, but we can't get any other way until we hit a vertex. So Q to R, that's there. And can we go Q to P? Well, yeah, but we've already done that. Can we go Q to T? Around the outside doesn't work, but if we go through the middle, we can get from Q to T. So there's one path there, and that's this one arching over the top. So we did Q to R, Q to P, Q to T. We need to say, can we go from Q to S or Q to itself? So Q's got no loop. That doesn't work, but I think we can go from Q to S this way. So we'll link those two there. And I think that's all for Q. We've exhausted it. So we've done P, we've done Q. Let's look at R. Okay, looking at R, looks like we can get to Q and we can also get to S, but we can sort of see everything else is blocked there. So we'll just stop. We've got R to S. Okay, checked off. So we've done P, Q, R. Now we're going to do S and then T. So looking at S, okay, S is connected to lots of things. We've already done S to P, S to Q, S to R. So we need to do S to itself, which I can't see a cycle here without running into a vertex. Don't think we can do it. So S can't loop, but S can go to T this way and this way. So there's 2 connections between S and T. Now we've got to the last vertex connecting T to everything else, but we actually don't need to because we've done P, Q, R, S all to T already. So we don't actually need to check that last one there. So we are done. Methodically, 1 vertex at a time to every other vertex, I think, is the only way to be sure that you get every connection here. And that's a time-consuming process. And if you get an exam question that only gives you a minute to do it, I think you've got to be budgeting time elsewhere. So anyway, that's my 2 cents. Let's move on. Here's a summary of Eulerian trails and Eulerian circuits with a few pictures to help you out there. Coming up next, we've got Hamiltonian paths and cycles, which are slightly more scary. Today's lesson is about finding a path that visits every location. If you're going to visit the Louvre and you want to see everything, can I suggest a really large breakfast? Because that place is massive. Also, pardon my pronunciation, I'm not as good at French as Tal Allenson. All right, exploring and traveling problems, part 3. This is the last one in this set. In today's lesson, we're looking at Hamiltonian paths, Hamiltonian cycles, and their applications. A Hamiltonian path passes every vertex exactly once. It cannot repeat edges, and it does not have to contain every edge of the graph. One of the things here, we're trying to visit every node, every vertex in sort of one continuous path. The tricky thing here with the Hamiltonian paths and cycles is that we don't have like a shortcut to see if one is there. So with Eulerian stuff, we could check the degree. We sort of had a tool to see if it was going to be possible and even an indication as to where to start and finish. But with the Hamiltonian stuff, we sort of can't do much better than trial and error. Technically, we could express like a formula or something by starting at one vertex and then trying everything and then starting at the next vertex and trying everything there. And you could, by exhaustion, figure it out. In this one, we're going to have to try and use our noggin to see the best one. And it won't always be easy to determine if it's there or not. I've got an example here, and the path I'm going to show you is C, B, A, D, E. So the Hamiltonian path is a path, and we're going to start at C, we're going to go to B, we're going to go to A, D, E. So that path there visits C, B, A, D, and E, which is every vertex in the graph, and it doesn't repeat edges, and it doesn't repeat vertices either, right? So we don't start and finish at the same place, so it's not a closed loop there. So that one is a Hamiltonian path. I also want you to notice that we didn't need to visit every edge. We can though, if we want to. Here's a word example. Determine any Hamiltonian path on the graph below. So the one I'm going to do, I think, is this one, A, B, E, C, D. That works. That wasn't too hard. There are others, right? I could start somewhere else. I could maybe even go around the outside and that would work. Great. On to Hamiltonian cycles. Our key takeaway today is that a Hamiltonian cycle is a Hamiltonian path that starts and finishes at the same vertex. We want to visit every vertex. We don't want to repeat vertices except the start and end one, and we don't want to repeat any edges. Notice that a Hamiltonian cycle does not need to visit every edge. I've got two graphs here. One has a Hamiltonian cycle and the other one doesn't. So this top one, if we go A to B to C to D to E, we need to go back to A there, finish the cycle. And the one below, we've got no Hamiltonian cycle present. You know, it's not possible. I'm telling you it's not possible. But if we try, I'll start at A and I'll go around, I'll go to B, I'll go to C, I'll go to D, and then I'll go to E. There's no way to get back to A without crossing through a vertex we've been to before, or passing over an edge we've been to before. You might think, oh, maybe you can start somewhere else. Maybe let's try starting at E. So if I try starting at E and I go B to C, D to A, looks like there's no way to get back to E without passing through B or D again. So I think no matter how hard you try, you won't be able to find a Hamiltonian cycle for that particular example. The worked example here is to determine any Hamiltonian cycle on the graph below. I can sort of see an easy one, so I'm just going to do an easy one. A, B, C, D, E, A. Hamiltonian cycle. Did it. Here's our last KU, applications of this. The types of walks along a graph and network we've seen can be found in lots of different applications. Common examples include finding the best route from one town to another and evaluating social networks. At your age, you're probably driving a car, and when you get in and think about where you're going, you usually try and think about what's the best way to get there. So that can sort of be modeled in this stuff that we're doing here. We've got a picture of a phone here working out some distance between locations. Google Maps or whatever navigation you use is going to be using some computerized process of these algorithms to find the best way there, right? Part of our job will be to try and determine some of these ourselves in the exam. So cool stuff. You know, we use it every day on our phones. So there's a summary of both of those new ideas today. I think the big challenge here is not to be able to do it isolated, but to look at graphs in general and decide, can you find an Eulerian trail or a Hamiltonian cycle or any one of those options from any one graph? When we group these questions together, when we know what's coming, it's a little bit easier. But if you're just given a graph in an exam context, you got to figure out, are you that good yet that you can determine these sort of on the fly? All right, coming up next, we've got minimum connector problems, and we'll leave this summary section here for you to take some notes if you'd like to. All right, what's the fastest route to finish your Edrolo homework? I've got a feeling it might be this, but I'm not convinced it's the most effective. Hi, welcome to the lesson on minimum connector problems. In today's graphs, we need to look at trees, subgraphs, and spanning trees before we can look at weighted graphs and minimum spanning trees or Prim's algorithm. Let's dive in and sort it all out. All right, trees. I think you might remember what they are from last year. Let's go over it again. A tree is a graph in which all vertices are connected by as few edges as possible. This means that a tree cannot contain loops, cycles, or multiple edges. And by that I mean, if you have two vertices, you can't link them with more than one edge. We've got a formula here that says that trees, if we've got a number of edges, that's equal to the number of vertices minus one. So here I've got some pictures of things that trees can't contain. So this first one here, trees can't contain cycles. So that cycle is here. So we've got too many edges there. So that's not a tree. Trees can't be loops. And so this other top picture here, it's got a loop at the top. So it's not a tree either. We need trees to be connected. So all vertices must be connected to an edge. And we can see that there's a disconnect here in this part of the graph. So that's not a tree either. In this fourth picture, we've got a multiple edge between two vertices. So these two here, there's two edges. We can't have that if the graph's going to be a tree. So that one's not a tree. So the only picture here that is a tree is this one. All right, so that's a tree. I want us to look at this formula of E equals V minus 1 to see why it makes sense. All formulas in maths need to be proved, and or at least all theorems need to be proved. And I think this one's not so hard to just get a feel for why it must be true. So if I start with the most simple graph, I think that would be this connected vertex. Just one dot is the simplest thing we have. And say I want to build up a bigger graph. Well, I'd have to add, I could draw a loop, I suppose, but I could draw just one more vertex. And then if I want it to be connected, I've got to connect them with an edge. So notice in this very initial state, first we had, just one vertex, and one less than that is 0, so no edges. So that has 1, v equals 1, and edge equals 0. And notice there's a difference of 1 there, even that most simple graph. So I think technically that would be a tree. So here we've got 2 vertices and 1 edge between them. Say I want to keep building it up. Each time now that I add a vertex, I must add an edge. And so because we started one behind, there'll always be a difference of 1 if we've got a tree. So just to really solidify that, watch how if I add one more vertex, I must add one more edge. And you can see there's, in this case, we've got 3 vertices and 2 edges. And so again, they're separated by 1. Hopefully that makes sense. Let's move on. Right, this brings us to subgraphs and spanning trees. So a subgraph is a graph formed from components of a larger graph. So here I've drawn an original graph of like a pentagon with a line going through it. And on either side, I'm showing you spanning trees and subgraphs. So what's a spanning tree? It's a subgraph and a tree that connects all the vertices in the original graph. So let's slow down a bit. Okay, so here's the original graph. A subgraph is just parts of that graph sort of taken away. So here I've just taken that triangle at the top, and that's a subgraph. And here's another one. I've taken this outside part of the graph of that, like I guess the trapezium or whatever. And so that's a subgraph too. And there's lots of subgraphs that we can form from that original graph. Now, what makes a subgraph a spanning tree is if it connects all those vertices in the original graph. So here we can see that in each of these spanning trees, I still have kept all of these nodes. So all the original nodes are in there for it to be a spanning tree. Notice on the left, these are not spanning trees because I've dropped some of the vertices. Right, so hopefully it's not too hard to see. You can always overlay a spanning tree, if you keep the dimensions right, and you should be able to see that it's like letting you get everywhere. I guess the name makes sense, like you're trying to span the whole graph. You need to get everywhere from at least one point. So, if I draw that top one, you can see we've just dropped 2 edges, but we can still get everywhere in the graph. Okay, we're getting closer and closer to the central idea of today's lesson, which is to find sort of the best spanning tree that we can. Here our KU is weighted graphs and minimum spanning trees. And so let's dive in. Our key takeaway is that a weighted graph has numbers attached to each edge, and they're called the weights. Also, a minimum spanning tree is a spanning tree with the lowest total weight. So if you can find a spanning tree, the best one is the one with all the lowest weights, or that best one is the minimum spanning tree. So I've got an example here, and we've got sort of our original graph up the top, and I've shown 2 examples of spanning trees here. So if we ditch this edge here with 6, and we choose one of these edges of 3, then we can get one of these graphs. So both of these are minimum spanning trees of the original. We can see here, we can find the total weight. So let's do that. So what's the total weight? 1 plus 3 plus 4 would give me 8 plus 5, I think is 13. Let's check the total weight is the same for the other one. So this one over here, I think we've got 1 plus 3 plus 4. Again, that's 8 plus 5, again is 13. Okay, so there's not always one minimum spanning tree. You can sometimes find multiple. Okay, here's a worked example. I'm to find any spanning tree of the graph below and then calculate the weight of that spanning tree. We're about to find out how to do this with an algorithm, a set of steps that always gets us the answer. However, sometimes we can just do this by looking at the graph. And something that sticks out to me is that edge that has a weight of 9. I'm going to have to get rid of some edges to get my spanning tree, and that one is a strong candidate to get rid of. So I'm going to start by maybe drawing out all my vertices. And I think, I've got 3 vertices. So in the end, I only want 2 edges. Remember, a spanning tree is going to have one less edge than the number of vertices. So I've sort of got to find the best edges that connect this graph. I think that that's going to be, all the loops are going to disappear. So I don't want to take the loops. I'm going to take this edge here of 2, and then I've got to find the best one. And I've got a choice of 5 or 6. And so obviously 5 is smaller than 6. And that gives us our spanning tree there. So its total weight is going to be 7. Okay, on to Prim's algorithm.
A key takeaway here is that Prim's algorithm allows us to find the minimum spanning tree of a graph. So it's a set of steps that will always get us that minimum spanning tree. Our steps I've written down here, sort of simplify them. There's probably some in your textbook too. It says choose any starting vertex. Secondly, inspect all the attached edges and their weights. You want to choose the edge with the least weight and attach that new vertex. Then you repeat step 2 until a spanning tree is formed. And just keeping in mind, if you've got 2 choices with the edge that have equal weight, you can choose either one. You might just get a different spanning tree, but it will still have the minimum weight. All right, so I'm going to do it here, and I can start anywhere I want to. So I'm going to start at the bottom vertex today, but I could choose any of them. And I'm just going to inspect all the edges that are attached to that vertex. I can see it's 5 and 6, and 5's lower. So I'm going to choose that one and connect it to this vertex. Now I need to reevaluate, look at all the edges that are connected to all the vertices I've chosen. So I've got this vertex here and this one here. And so all the edges attached to them are the 4 and the 6, and I have to choose the lowest one. So I choose 4, and I've connected this new vertex here. Again, I look at all the edges connected to the selected vertices. I've got a choice of 3, 3, and 6. So I can choose either 3 here. I'm just going to go straight down. I could choose the other one, but I'm just choosing that for now. And now I've just got one vertex left to connect. And to do that, I've got a choice of 1, 6, and 3. So I have to choose the 1, and that gives me my spanning tree there. Okay, looks like we got it right. What I'm going to do now is I'm going to annotate from a different vertex and show I can get this same spanning tree here. Just note though that I could have, instead of this one, it could be down here too. That would be okay. And now I'm going to do the same problem, but starting from the top this time. Okay, you'll see I make different selections, but end up with the same graph on the right. So if I'm looking at that particular vertex I've chosen now, so I'm starting again, I've got a choice of 4, 3, and 3. So I can choose either 3. I'm going to choose this one because that'll make it look the same as my solution there. And then I've got a choice of 4, 3, and 1 to connect a new vertex. So I choose this 1 and connect to this vertex here. Okay, now I can choose 3, 6, and 4. And you might think that I choose 3 because it's the lowest, but it doesn't connect a new vertex. So I can't actually choose that one. We can't choose an edge that connects already connected vertices. So that's a wrong move. We can't do that. So I have to sort of look for the next one now. So I can see 6 and 4. Well, 4 is my best bet. And then I can choose 5 or 6 to connect a new vertex, and I choose 5. Okay, so we see from starting at a different vertex, we still generate the same spanning graph. So just pick anywhere, doesn't really matter. Okay, let's move on. Here's our next worked example. It says use Prim's algorithm to find the minimum spanning tree below. So I'm just going to jump in and do it. I'm going to choose any vertex, doesn't matter. I'm going to choose, I sort of like to choose one near a low number. This is what I do. You can do whatever. And I can see right now I need to choose the 5, the edge with the 5 on it, and connect it here. And now I can sort of choose from here, here, or here, right? So I got 20, 30, or 10 to connect a new vertex. And definitely the best option there is the 10. So let's choose that one. Got new choices now. Now the 20 is the lowest, but it doesn't connect a new vertex, so we don't choose that. We can choose 30 or 40. So we have to choose 30, and that connects this new vertex here. And now I've got 10, 15, 20, 40. I have to choose 10, and then I have to choose 15. So that gives me my spanning tree there, and you'll see that I've connected all the vertices, and so then I sort of know to stop. There's the answer without everything cluttering it. It doesn't ask me to find the weight, but we might as well find it there. What's it going to be? 10 plus 15 is 25. Plus 30 is going to be 55, 60, I think a total of 70 there. There's a summary slide for you to take some key notes if you like. Prim's algorithm there is important that you can use it, so you probably want to add that to your bound reference. Up next, we've got the flow problems, so I'll see you there. Hi, I'm Michael Palmer. Welcome to our lesson on flow problems. Today, I've organized a video. I really like this YouTuber. He does lots of great stuff. So check out his perspective on flow problems if you're interested. Okay, lots of KUs today to help you step through these ideas. First one's maximum flow. Next one's source and sink. And the third one's cuts. We need those concepts to figure out cut capacity and the minimum cut, and also the maximum flow, minimum cut theorem. So there's a lot there. Let's go through piece by piece and work it out. Okay, on this slide, I've got 2 pictures to help us think about maximum flow, this concept of water flowing through pipes. The flow of water through a pipe can be measured in litres per minute. How many litres are travelling through that pipe every minute. The maximum flow through a network is equal to the minimum capacity through a network. So let's unpack that. What does that mean? So here I've got a simple picture which is meant to represent pipes and water flowing through those pipes. And I want you to think about this concept of bottlenecking. I guess where that term comes from is sort of a limit on the amount of water that can flow through a connection of pipes. So here, if you imagine, say, this top one, if this one's your water bottle, and you're trying to pour the water out of your water bottle, you probably know that if you cut off the nozzle, the water would come out faster. In other words, this narrower pipe here is making sure the water flows through slower. This other option here, you could think about trying to fill up your water bottle. So if a hole for your water bottle is about the same size as the stream of water coming out, and you realize if you had more water coming through, you still wouldn't be able to get it in any faster because there's a bottleneck. Right, so in both of these examples, the water can only flow through at 5 litres per minute. That's the minimum capacity there through this network, right? So we sort of only move as fast as the slowest member, right? People use that analogy in teams. We only go as fast as the slowest member of the team. Or, with these pipes, the water can only flow through as fast as the minimum capacity pipe. Cool. Let's move on. We need to think about the concept of a source and a sink. And the source in our problems will be where the water comes from, and the sink will be where it goes. Just like in your house, when you turn on the tap, that tap is the source of the water for us at home, and the sink is where it leaves. Once it goes down the sink, we can't get it back. So here we've got the key takeaway, which says the network diagrams that represent flow problems contain vertices representing the source and the sink. They should always be labeled on these types of problems. Notice that this is a directed graph, so we only let the water flow in one direction through the network. The source is the vertex where the flowing substance, which can be water, cars, or people, originates. And the sink is the vertex to which that flow is occurring. Okay, let's talk about cuts. In order to think about what is and isn't a cut, you sort of need to imagine the water flowing through this diagram. So our key takeaway says a cut is a line drawn through a flow network that separates the graph into two parts. Not only this, to be classified as a cut, this line must separate the source and the sink completely. A cut models how to stop the flow in a network. So here I've got two lines, one is a cut and one isn't. So here's a cut, it separates the graph into two parts. If we try and visualize the water flowing from the source to the sink, we'll notice that that cut blocks us off. Water coming out gets stopped here before it gets to E, but it could still go around the other side. So let's see if it can get to the sink. No, it gets stopped between B and C and between B and F. So because this line completely stops all the water from the source to the sink, it's classified as a cut. This purple line is not a cut. Well, how can I tell that this is not a cut? Well, I can still get water from the source to the sink. So imagine this orange line isn't here. Okay, I get stopped this way, so I get blocked here and here. So it does its job there. However, I can still get water to the sink around the other way. So if I go from the source to B, to C, to the sink, I've actually been able to push some of the water to the sink. So that means the purple line is not a cut. Okay, on to our next key understanding, cut capacity and minimum cut. At this point, you might be wondering, what's the point of having a cut? Why do we need it? Well, if we analyze the cuts properly, it can tell us the maximum flow through the network. That's the theorem that's coming at the end. For now, let's work out on working out the capacity of a cut. So we know that a cut must block the source, flow from the source to the sink, but the cut capacity is the total capacity of all edges that a cut passes through. However, if one edge in the cut prevents flow from the source to another edge, the blocked edge will not be added to the cut capacity. That second sentence there, I'm going to show you what that means with an example here. So, okay, I've got a cut capacity example. I'm going to draw a few cuts, and I'm just going to draw a really simple one here. It's really clear to me that I could cut all the flow off by doing a cut there. So let's call that C1. If I work out the weight of C1, or the cut capacity, this is equal to the weights of all the edges I passed through. So I've got 14 plus 20. That gives me 34. Okay, so I found a cut. There are other cuts I can find. So I'm going to take another one. C2 is going to go through here. Okay, let's call this C2. You might think that the cut capacity here would be 14 plus 13 plus 17 plus 15. But that's wrong. And the reason that's wrong is because we imagine the water passing through from the source to the sink, then we'd come down through here and we'd get blocked at E. And there's actually no way to go from E to F if we've already been blocked. So we're not going to count that weight there from E to F. So we won't be counting this 13. There are other ways to determine which things we will and won't cut. Some people like to imagine a car driving through along this line. And if the water goes in to the left side, into the passenger side, then you will count it. And if it goes into the right side, then you won't count it into the driver's side. But I don't really feel that I need that to work it out. And I think I can just think about, well, has this water been blocked at an earlier edge? So we won't count the 13. And so the cut capacity of cut 2 is 14 plus 17 plus 15, which works out to be 46. Okay, so you need to think about all the edges you pass through. Have you blocked that off in an earlier part of your cut? All right, in a flow network, there can be lots and lots and lots of cuts that you can find. And we're trying to find the minimum cut. That is that one with the lowest combined total weights. So I'm just going to draw a bunch of cuts on these two diagrams here to show you how many there can be, and that this can actually be quite a time-consuming process. So I'm going to start going through this edge here first. So I'm going to call this cut 1, and I'm just going to cut off those two. That's a valid cut. It separates the source from the sink. And I'm going to do another one here at C2. And instead, I'm going to go through this edge first, but then instead I'm going to go through B to F and B to C. I'll call that cut 2. And then I think I can see another option there. So instead of that, I'm going to do cut 3, goes sort of the same way, except then we go through C to the sink at the end. And that works. But I can see other ways still. So I'm going to take C4 and it's going to go through here and then back up here. So you can see it's getting pretty messy, and I've only started going through one option. If I then instead decide I want to cut down this way, I'm going to start here and, that's actually the same as cut 1. So that's not new. So let's find a new one. I think maybe I could go this way. Okay, I think that's a new cut there, C2. And I could also maybe loop around this way. That's cut 3. I could start up here, maybe different color again. I could start up here and travel down this way. That could be cut 4 and so on. And so you can see there's lots and lots and lots of cuts that I could do. And we're trying to find the lowest one. That's not easy. Let's move on and let's see where the lowest one is the minimum cut for this example. Okay, my key takeaway here is that there can be many cuts in a flow network diagram. The minimum cut is the cut with the lowest total weight or total capacity. Okay, there can be more than one minimum cut, but if you can find more than one, they'll have the same total capacity. They have the same weight. Turns out in this example, the minimum cut here is just here, and it has a total capacity of 34. All right, this is really where we've been heading the whole time. It's the maximum flow minimum cut theorem. What this means is that if I can find the minimum cut, that tells me the maximum flow through the network. So there it is stated. The capacity of the minimum cut in a network is equal to the maximum flow through that network. And this ideally is what we want to find in these sorts of problems. This is the same example I used earlier in the slide, and you might remember that the minimum cut was here and its capacity was 34. So if this is in liters per minute, the maximum flow of water through this network is 34 liters per minute. However, finding the minimum cut can take a long time. It can be tricky, and there's no real way to know when you've actually found it. Just because you haven't found a cut that's smaller doesn't mean it doesn't exist. And so when we do these problems, we can feel a bit uneasy about whether or not we've found the final answer. What I'm about to show you is a method of trying to feel confident about finding the minimum cut. And it's not foolproof. It won't work every time. Sometimes you have to start again and use a bit of trial and error. So let's have a look. Just getting rid of that minimum cut there so I can draw on this diagram. What we're going to do is think about how much water we can push through this network. And we're going to think about pushing the water. And that's sort of how we're going to work around this problem. We're also going to try and look ahead at the diagram, sort of get familiar with it, and see if there's any bottlenecks. So it's pretty obvious to me that out of this source, from just the initial sort of my initial lookings at it, I can push 20 liters out of one direction and 14 out of the other. And so I'm sort of scanning ahead, and I'm looking at how much can come into the sink from this end here. And 18 plus 17 plus 16, to me, is that more than 34? So, okay, it looks like we can push all the water through to the sink. So we should be able to get everything through. Let's see. So let's imagine I push 20 liters out here and I push 14 litres out here. So I've drawn a little line, and that second number is indicating how much water I actually can push through that network. I'm going to follow this top path, and if I push through here, then I can't actually push all 20 litres through this B to C pipe because it can only take 15 litres per minute or whatever. So I'm going to push as much as I can through there. I'm going to put a 15 there. And then as I follow this through, if I only push 15 litres through BC, I think that I can only push 15 litres through C to the sink because I don't have 18 litres to push through. So I'm going to put a 15 there. So I'm not using that link from C to the sink. I'm not using its full capacity, but that's okay. So in this connection here, the flow into the network can't exceed the flow out of the network. So I've put 20 in, I'm only getting 15 out, but I have to push that other 5 litres, I think, down through this path here. So I'm going to push that 5 litres, and that sort of works out. My flow coming out of vertex B is 15 plus 5 is 20, so that was there, and my flow coming in is 20, so they're sort of matching. Okay, I'm going to follow that flow through from B to F, so I've got 5 litres flowing through from B to F, and I can push another 5 litres, I think. Well, the only way it can go is from F to the sink. So I'm going to put a 5 here. And so now all the water flowing from the source to B, I think, has been accounted for and is going into the sink. So I've sent 20 from there, and I'm sending 20 to the sink. Okay, so now I'm looking ahead, I'm looking back, and I can see this path here going down now. So I'm going from the source to E, and I'm pushing 14 litres through there. And okay, well, I've got two options. I could push 13 through E to F, except then I haven't got 13 litres left to flow through from F to the sink. I can't fit it through here. So that's not how the water is going to flow through a network. I don't think we can imagine fitting more water into a pipe that can't take it. So we're going to instead push 14 litres through the 16 litre pipe, and I'm not going to send anything through the 13 litre pipe. Now I could send some through each of them, but this is sufficient to solve my problem, I think. So now what you'll notice is that every edge I've actually indicated how much water I've actually got flowing through. The original numbers represented the capacity, how much water could be pushed through. But my second number represents my idea of how much I'm actually sending through that network. This method now lets me find the minimum cut. All I have to do is circle the edges where the capacity is equal to the water I'm actually sending through. So what I mean by that is this 1414 and this 2020 here, they are telling me where my cut should go. That's where the maximum flow is occurring. So my cut just passes through them, and I'll call that cut 1. And that is equal to 34. And that's how I can sort of deduce the maximum flow. I think it's important for you to have a go at this sort of method as you work through your problems, because when we get to bigger networks, it becomes harder and harder to really be sure we've found the maximum flow. I should point out this method you can still make mistakes in it. It is a bit of trial and error, and sometimes you have to go back and start all again. So it's not bulletproof. Finally, I will tell you that there is an algorithm to work this stuff out. It's called the Ford-Fulkerson algorithm. And if you're into computing and stuff like that, you might like to go and have a look yourself. But it's not in the VCAR course, as far as I can tell. Okay, technically that's it for the theory, but I wanted to include one more worked example because this one was on an exam, and I think it was quite difficult to figure out just with the minimum cuts alone. Just looking at the diagram, there's probably lots of cuts you can see there. And one thing to do when looking at a problem like this is to just spend some time looking and thinking about the water flowing through this network. Let's read it, and I'll try and give you a worked solution to this problem. Okay, the network diagram provided shows the local road network of town M. The numbers on the edges indicate the maximum number of vehicles per hour that can travel along each road in this network. The arrows represent the permitted direction of travel. The vertices A, B, C, D, E, and F represent the intersections of the roads. Okay, so we've got some flow problem. Part A says, determine the maximum number of vehicles that can travel from the entrance to the exit per hour. So we've got vehicles per hour as our measurement. And as I work through this, I might just actually say water because I'm thinking about water flowing through. It's the same sort of thinking that we use. So this is not such a big deal on what's flowing, more that we're just thinking about flow in general. Okay, so I'm supposed to find the maximum number of vehicles that can travel from the entrance to the exit per hour. And, I know where the minimum cut is here, but, when you're doing the problem, you don't know in advance. So I'm going to use this pushing the water through algorithm thinking, trial and error process to try and solve this problem Okay, so what I can see is I can send 1,500. So here's our, this is our source and this is our sink. And I can see I'm sending 1,500 in and I'm putting 1,500 out. And so, it's possible that if there's no bottlenecks, we could send 1,500 vehicles per hour through this network. But I think what we'll find is that there are some bottlenecks. So let's sort of look for them. If I think about going through this network, I'm going to get to A, and then I can go through to D. So if I think about some paths going through the network, that might help. So I could go along this way. If I'm traveling sort of directly to the sink, I could go there. And what's weird about this is that between B and C and A and B and A and D, the cars can sort of cycle through here. So technically, this path I could send back up along to B, and I could actually do a big pointless loop if I wanted to. And that makes this a little bit hard to look at. So that's possible, but I don't think that the cars would want to flow that way if we're trying to get them to the sink. So I'll keep it in the back of my mind. But the other main path I can see is sort of, flowing down here and then flowing up the top towards the sink. And I could sort of take a detour down here for more water to flow through. So that's, sort of just generally how the water or the vehicles are flowing through this problem. Okay, so let's get rid of all that and let's start to think about some restrictions. So if I flow 1,500 down here, I can send 650 this way and 700 this way. So what's that? 700 plus 650. I think that's going to be, how much is it? It's 1,350, right? Okay, so I definitely can't send, at a maximum. I think I'm probably sending 1,350 here. That's my initial estimation of how much I can actually push through town M. So we've already cut off 150 vehicles per hour. Okay, so, let's imagine I do that and I send 650 through here and I send 700 through here. Well, if I look at this top path, I can see I'm actually bottlenecking at the top here at 680. And so I'm actually going to adjust my numbers again, and I'm going to change that to 680, which forces this to be 680. And now I've actually got 20 vehicles less going through. And so I'm going to adjust here to be 1,330. So I've just taken 20 off there. And I think that's a pretty good start. And so let's see if we can get all the water through from here. So if I flow 650 through this bottom path, then I think I can probably send 650 along up here. And I've got 680 flowing into C. And I reckon I can probably get all that out. If I flow some out this way, 620, I'm going to send 620 along that top path. So I've got 40 litres left to send through to E. So that's going to be 620 plus. So the flow into C is going to be equal to the flow out of C. So I think I need to send 60 through C to E down here. Okay, that seems to be working. Now into this node here at E, I've got 650 coming from the bottom path, and I've got 60 coming from the top path. And so putting them together gives me 710 flowing through E to F. Then I've got 620 flowing in from C to F, that top path along here. And so if I add those together, what's that? 620 plus 710 is going to give me 1330, making sure that doesn't look like a 1. And that is starting to look pretty good to me. Now, I've sort of managed to, I'm going to clean up this annotation a little bit so we can look at it. So yeah, that's a bit better. Now, you can see that I use that sort of methodical thinking of pushing the water through. And I'm pretty convinced, I hope you are too, or maybe you could get here yourself, that all that water is going to flow through from the source to the sink. What I'm going to do now is I've accounted for all the water that can flow, and I'm just going to close off those pipes with a 0 that sort of indicate we've got no backflow or anything like that. So I don't think anything's going to flow through this pipe or this pipe or this pipe or this pipe or this pipe. Okay, I think that's looking pretty good. And now that I've done that, I can use my trick to find the minimum cut. And so I can see, I'm going to use a different color for this. I'm just going to circle those pipes that have the capacity matching their flow. So we're sending as much water through there as we can, or vehicles through there as we can. So I've got that top one BC, and I've got this one here. And actually, I think they're the ones at maximum. And so my cut must pass through them. So I'm drawing my cut like that. Okay, so there's my minimum cut. And now just think about, can the water actually get there? Should I count that edge? Well, yeah, I think it's separating the source from the sink. It's cut it off, so it's a valid cut. I think that there's no water flowing through here, and that's indicating that if I wanted to come through here, I'd actually have to go around this way, but I'm already blocked from that path. Okay, so that doesn't work. So I don't have to count these parts here in my minimum cut. So my minimum cut is equal to 650 plus 680, which I think we worked out before is 1330. So my maximum flow of vehicles per hour is 1,330. Okay, notice that I did a trial and error method here, and it wasn't a perfect algorithm, but we did manage to get the correct final answer. Let's move on. Okay, on to part B. Let's have a read, see what it wants from us. It says the local council plans to increase the number of vehicles per hour that can travel from the entrance to the exit by increasing the capacity of only one road. Okay, so we're trying to increase the number of vehicles per hour, and we can only change one road. Part 1 says, complete the following sentence by filling in the boxes provided. The road that should have its capacity increased is the road from vertex something to vertex something. Okay, in this example, I think knowing where the minimum cut is helps us. And so I think from the last part, we've determined that the minimum cut should be through here. From the maximum flow minimum cut theorem, we know that the flow through the network is being restricted by something on that minimum cut, right? So the maximum flow is sort of the slowest through, like the flow through the slowest part of the network. So it's either from AD or BC. And actually, we could increase the flow on either one of these to increase the flow through the network. I'm going to look at the wrong answer first. So we could choose BC. We should be choosing something from this minimum cut. So that's either BC, which is here, or AD, which is here. I'm going to draw the flow sort of from the source to the sink going through BC. And if I do that, I sort of travel this way, and then it comes up here. And notice that that number there is 680. Okay, and then if I flow through, I'm actually sending 680 through BC, and then I'm splitting it off CF. I'm sending 620 through CF, and then I'm sending 60 down to E. Okay, and then part of that flows through EF, and I guess all up, we're sending a total of 680 along that path to the sink. And so if we increase BC, which is on our minimum cut, then I think we need to think of, would we bottleneck anywhere else? And so if I increased it by 20, right? So if I increase this to 700, then that's the reason I've chosen that is because it would start bottlenecking here as well. So we'd have to increase AB as well in order to flow any more than 20 vehicles per hour through there. And so that's one option. So that's pretty much as I can increase along BC, and that's possible. And now I need to check AD to see if I can do any better than that. So I'm going to clean up the diagram here. So for part 1, I guess we've got an option. Could do BC, which increases by 20. Okay, so that could work, but maybe we could increase AD as well. And we're going to consider the flow through AD from the source to the sink. So it's coming out of Town M entrance, going through AD. Some's going up to AB, but we're looking through here. We send 650 through DE, and then that meets up with the rest of the flow from above, and looks like we're sending 650 through that bottom path. Okay, and so we've got some options here to increase. So we could increase 650, and if we do, can we keep flowing water through? So let's say, why don't we just see if we can beat BC? We don't have to beat it by a lot, but let's just say 30. What if we increased it by 30? Could we put it through there? So, that would change this to be 680, so I can only change one. And could I get the rest of that water through? Well, I think that I could. Yeah, I could. I could send 30 more. I was sending 650 through DE, and so I could send instead 680 through, and then that would make that 740 sending through. So yeah, I can get it through. And so that means that I could only increase BC by 20, and I've beaten it by increasing pipe AD. Because I know that the increase has to lie on that minimum cut, I can conclude that AD is the correct answer. So I've cleaned the answer up a little bit there. I've put in A to D. I've deduced that must be the answer, but I haven't yet deduced exactly how much I can increase it by. And that's the next part of the question. Right, so I've got to figure out how much I can send through. So I've definitely decided I'm going to send vehicles through AD, and I'm just going to think about the paths I could send them through. So, okay, I'm sort of ignoring that top path because that's sort of sorted. I'm not going to change anything happening there. I'm going to change this. And so where can I push my vehicles? I can push them through D, and I can send some up there. and then I've got plenty of space to send them through CE. So I can send some more that way, and I can send some more through DE. Those are actually my, that's fine. They're the only paths I can take, though, before I'm interfering with that top flow of the vehicles. And so then I can send through EF, but I couldn't send any up through CF. That was already taken by the top flow, that sort of top path. So that's sort of where I can push the water. And so I've decided I'm going to change AD. And now the question is, well, how much can I increase it by before it starts being gated? So, okay, well, let's look at how much the rest of the pipes can take. I think I'm already sending 620 through here, and through this way here, I'm sending a total of 710, right? And so what's left? Well, I can see that there at EF. I'm going to write that down. I think at EF, I can increase there. If I take 710 from 840, that's going to give me 130. So along that pipe, I can flow an extra 130 vehicles per hour. So can I get them there? I think that's the most I can do. I can't do any better than that because all of my flow must go through EF from that bottom path. So 130 seems to be the best I can do. I know the only question is, can I get it there? Can I increase AD to allow 130 through? So can I get it to EF? Well, I think I could. I've got heaps of room on CE. What's left? I can send another 320 minus 60, I think is 260. I can definitely fit 130 more through CE. And all that's left to ask is, can I send it up through DC? Well, I wasn't sending anything up through DC yet, so I can send all that water up through there. So yes, I can get 130 litres to EF. And to do that, I just need to increase AD by 130. So I'm going to increase AD by 130 vehicles per hour. Now, let's read back and make sure we've answered the question. So part 2 says, what should be the minimum capacity of this road to maximize the flow of vehicles from the entrance to the exit? Okay, so I've got to increase 650 by 130. So with all that work, let's make sure we do the arithmetic correctly. So AD is increased to 780 vehicles per hour. And that's the answer. Only 6% of the state got this question right. And I think unless you are using some sort of method like this, it's going to be pretty hard to deduce. If you know another way, great. But I think that's the best way I've come across to figure out the answer. There are other VCAR questions like this, so this isn't the only opportunity to practice this type of problem. Here's a summary of all those key points we looked at today. Hopefully you understand what's going on with pushing water through pipes or things other than water. Up next, we've got shortest path problems. We're going to leave this slide here for you so you can take some notes if you'd like to. Thanks. Today's lesson is all about finding the best path or route. If you ever decide to travel through Europe, there'll be a best way to fly, bus, or train to get where you need to go. Let's jump in and find out how to find the shortest path. Hi, I'm Michael Palmer. Welcome to Shortest Path Problems. In today's lesson, we're going to look at doing shortest path problems by inspection, which you might have done in Year 11 class. And we're also going to look at Dijkstra's algorithm, which if you went ahead, you might have done, but that's the algorithm we use to get the shortest path every time. So let's have a look. Our key takeaway for our shortest path by inspection is that a graph can be used to represent scenarios involving distance, time, and cost. It's useful to minimize these quantities in real life because, well, everyone likes to minimize costs, time, or distance, right? So we can achieve this by finding the shortest path in a network. If we can model some real-life problem with a network, then we can use Dijkstra's algorithm or just inspection to find the best way to do it. Okay, here's an example. It says, let's look for the shortest distance from A to F by inspection. So I'm supposed to just look at this and try and find the best way to get from A to F. So I'm going to color in A and I'm going to color in F to see where I'm going. And I'm looking at it and, can't see it immediately, but my intuition's telling me that, well, I could sort of go up this way, and that would take 20, or I could go around the side here. 8 plus 11 is going to give me 19. So I get to E shorter going around that side there. So get rid of that. And that's looking good so far. I think I don't want to take any more steps. Like I don't want to do a zigzag because then I've got to do, that weight of 9. So that's looking pretty good so far to get to E. And then I've just got a choice of 5 or 4. Well, I take the shortest path there for 4. And looks like my shortest path is ACEF. And the shortest distance there, what should that be? Let's add them up. 8 plus 11 plus 4. Oh, that's it. Okay, so 15 plus 8, I think gives me 23. All right, let's look at Dijkstra's algorithm. Our key takeaway here is that Dijkstra's algorithm helps us find the shortest path from between any 2 points, any 2 vertices in a graph. So it's useful when the graph's really large because we can just run this algorithm, or If it was really, really large, we'd probably program a computer to do it for us. With this example here, we probably could do it by just inspecting the graph and we'd find it pretty quickly. But we're going to run the algorithm on this small example so we get a hold of it. Okay, so I'm just going to do it. We're going to find the shortest distance from A to F. In order to set up for a problem like this, you need to rule a table and put your starting point in this first row here. So we're starting at A, and put the other vertices in the columns. You don't need to put A in the column because we won't move from A to A. What we do is we start at A and we look at the diagram and say, well, where could we go? We could go to A, we could go to B or C. And so to get to B, I can see that would take a weight of 10. And to get to C, that would take a weight of 8. And I can't directly get to D, E, or F, so I just put a cross in those boxes because I can't get there yet. What I do now is I need to choose the lowest value in this row, and I can see that's 8. So I put a box around 8, and I move it down into the next column, and I'm going to put that column header, which is C, in my next row. Now, you don't have to do anything more there, but you can actually fill those 8s down, because once you sort of make this selection, we never come back here. We never sort of reevaluate a path to C. So we're going to just put those numbers in the box there. Some people just scribble out the columns. That's sort of what I like to do, however you want to run it. But we can do this now. And now we sort of think about, well, we've gone from A to C, and that's taken us 8 units or whatever, or a weight of 8. And now we look at, well, where else can we go from here? From C, I could go to B or E. It's already taken me a weight of 8, so going to B would take me 8 plus 9, which is a total of 17. But that's actually lower than the value above. So we're not going to put 17 in the box. We're going to take that lower path to B, which is straight from A. So I'm going to write in here 10. That path didn't matter through C. Okay, can I get from C to E? That's the other one I can do. Well, I went through A first, and that cost 8. And then we've got a weight of 11. Putting those together gives us 19 to get to E. Cool. Okay, I can't get directly to D or F, so I'm just going to put a cross in those boxes. Okay, great. My next step is to choose the lowest value, which here we can see is B, and I fill that down. Okay, and I put the column header in the next row. So I'm going to put B there. Okay, and now I think about how I've traveled to B along that path. Well, I chose 10, so the better path was just straight from A to B. Okay, you don't have to keep redrawing on the diagram. I'm just doing that to help you see what I'm doing. So I go from A to B for 10, and then I'm at B, I can get to C, E, or D. So what's the cost of going there? Okay, if I want to go to D, that's 10 plus 12. I can finally get there now. So that's going to be a weight of 22. If I want to go from B to E, that's going to be from A through B, that's 10 plus 10. That gives me a weight of 20. Oh, except that's higher than what I had above. So I'm actually not going to put in 20. I'm going to copy down the lower path to C, which was just A to C. Okay, so I didn't put that 20 in. I've just put the 19. Can I get to F? No, I can't. I go A, B. Oh, there's no way to directly get there from B, so I just put a cross there. Okay, I looked at the unboxed numbers, and I choose my lowest one, which is 19, and I fill that down. Okay, then I'm going to put the column header, which is E, into this row. Okay, so now I'm thinking about that shortest path that I got to E, and that was A, C, E, I think, and that was the total of 19. So it's 19. That's the best way to get to 19, costs 19 units, or its weight is 19. And now I need to look from E, where can I go? Well, I can go to F. I can finally get to F. So if I go that way, it's 19 to get to E, plus 5 to get to F is going to give me 24. Can I get to D? Well, I actually can't get directly to D from E, but I had done so previously. And so even though I can't get there, I don't put a cross. I just copy down that number from above. I know already that I can get to D for a weight of 22, so I put it in. Okay, next step is to look at the lowest value, and I can see that that is 22. So I fill that down, and I'm going to put the column header of D into my next row. Okay, there it is. Okay, so now I'm thinking about I got to D by whatever path, doesn't really matter, but I know it only costs me 22. And from D, I can get to F for 5 more. So I add 5 to 22, which gives me 27. But that's actually higher than the value above, which is 24. So I'm going to put in that value from above, which is 24. That's the fastest way to get to F. And that's the only one left. It's my lowest value. So I put a box and I fill it down and fill in my last column header in my new row. Okay, that's the algorithm complete. And so what we're going to do now is evaluate the shortest path and work out that shortest distance. All right, so if we've got to this value here for f, and I follow that path up through 24, I got to my highest 24. So I start here at f, and I sort of travel up as far as I can see that same number. So I get to 24 here, and then I go across to whatever letter is here. So I'm going to go across to E, and so I find 19, and then I go up to my last 19, and then I've got to C. So I go across from E to C. So that value there is 8. And then we're going to move up to the highest value of 8 we can see. So that 8 stops there, and I can go across to A. And so then I can look at the horizontal lines, and that gives me my path. So I can see A, I have a horizontal line there, C, E, and started at F. So my path is A to C to E to F. Okay, and looks like my minimum weight to get there, or the shortest distance there, is 24. All right, we did it. All right, let's use Dijkstra's algorithm to find the shortest distance from A to I. We've got a diagram here. We could try and do it by eye, but we're going to use Dijkstra's algorithm and see if we need to follow it all the way through. We're going to see what happens when we just go ahead and do it. So I've set up the table here. We're starting at A. Okay, so we're there, and we're going to work out the shortest distance from A to I. So let's jump in. So if I'm at A, I can get to B and C for a weight of 40 and 8 respectively. But I can't get anywhere else, so I'm going to cross out all those other columns, right? So now I choose the lowest value, that's 8, and I drop it down. And last time I wrote 8s all the way down the column, but I'm just going to blank it out, and that's fine. You can do that too. Okay, so once I drop that 8 down, I'm going to put C in this row, and now I'm sort of thinking about, well, I've moved to C for a weight of 8. Okay, where can I go from C? Well, I can go to B, I can go to D, I can go to F, I can go to E. So let's see if I can do better to B, and how fast can I get to the other vertices there. So to go from C to B, I could do 8 plus 37, sort of along that way. That's going to be bigger than 40. So I'm just going to drop the 40. And then A to D, I've got to go, so I like to say I'm at C for 8, and then I need to add 5 to get to D. That's going to be 13. And I can add 10 to get to F, which gives me 18. And I can add 4 to get to E, which gives me 12. Right? Yep. Okay, so it gets me 12. And I'm going to pop 12 there. And I can't get to G, H, or I yet. I can't get to any of those. So I'm just going to keep putting crosses until I can get there. Okay, so look for my lowest value. That's E. Put a box around it, drop it down, put E in this row. And I'm going to black out this E column because we won't need it anymore. Okay. All right, so now I like to think, well, okay, so I'm at E, and it's cost me 12 to get there. Okay, so from E, I'm at E for 12, and I'm looking, where can I go? I can go to F, I can go to I. So I've got to add 2 to get to F. So I'm there for 12. To get to F is going to be 14, and plus 3, so 12 plus 3 is going to give me 15 to get to I. Okay, I can't get to G or H yet, so I'll cross them out. I can't get to D any quicker. I can't actually get to D from E, so I'm just going to drop that value of 13 down. And I'm not going to find a fast way to B from E, so I'm just going to drop that down too. Okay, so now I'm going to take my lowest value, which is 13, drop it down, add D, the column header, to my next row, and black out that column. Okay, so now we're at D for 13, so let's draw that in. So you might like to have a few diagrams or something if you want to work it out, or whatever works. So I'm at D for 13, and I can go to F, and that's the only one I can get to that's new. So from D to F, if I'm at D for 13 plus 6, to get to F is going to be 19. But that's actually higher than what's above. So I don't want to copy 19 in. I just want to take the lower path to F, which is 14. I can't get to I directly, so I'm going to drop that 15 down. And I can't get to B directly any faster, so I drop that down. Now the lowest value there is 14, so I box it and drop it and move that column header F into the row. I'm going to also blank out that column. So I'm looking at F for 14. I'm at F for 14, so let's draw that in so you can see where I am. I'm here. It took me 14 units to get there, or a weight of 14. And I can now go to G, H, I, looks like I can go anywhere. So let's evaluate. So I want to go to F. Can I get to G? Yes, I got a +7 from 14, so I can write a 21. And I can get to H for an extra 5, so 14 plus 5 is going to give me 19. And I can get to I for +3, so I'm at F for 14 plus 3 is going to give me 17, but that's higher than the value above, so we don't want to take it, and so we'll write 15 here in the box. Okay, so I still can't get to B, so I write that 40, identify my lowest value in that row, which is 15, and I drop it down and blank out that column. Now, actually, at this point here, we've got to I. We were trying to get from A to I, and we could stop the algorithm here. Looks like our shortest distance is 15, and that's the answer, which is cool, and we could even find the path. But I think to show you, I'm going to keep doing the algorithm all the way to the finish. All right, so I'm at I for 15, so I'm going to draw that in. So now I'm at I for 15, and I can get to H for one more. So 15 plus 1 is going to be 16. So that's actually lower than 19, so that replaces that 19. I can't get to G directly, so I just copy in that 21. And I can't get to B directly, so I copy in that 40. My lowest value is now 16, so I box it, drop it. I'm going to black out that column and put the column header H in the row. So do all that at once. And now I'm at H for 16. Okay, I'm at H for 16, and I look to G. I can get to G for 2 more. So 16 plus 2 is going to be 18, and that replaces the 21 above. And I can't get to B, so I'm going to just put a 40 there. Okay, so 18 is my lowest. Box it, drop it, black it out, and G in the row. Okay, and so now I'm at G for 18. But there's not much to do from here. I can't get to B, which is the only remaining vertex I'm trying to get to. So I just write a 40, box it, and drop it down. And so it turns out the best way to get to B was that 40 from A, which you can probably see from the start. Okay, so this thing shows you the shortest distance from A to any other vertex. We wanted to go to I, so I'm just looking at this column here, I. We're here at I, and we've got a 15, so we're going to move up until we stop seeing 15s. Okay, we're going to stop here, and then we're going to go across until we hit E in the column. So we look at this row, we'll have to go across to E. I go across to that column, and I see a 12, and so I'm going to go up to my last 12. And over here I can see a C, so I need to move across to column C. I hit an 8, I go up to my last 8, and then across to A. Okay, then it's just a matter of looking at the horizontal lines to tell you that path. So I can see there's a horizontal line in this column, and I is where we need to finish. So our path is A, C, E, I. And we can see that our shortest distance there is 15 units. Okay, we did it. All right, here's the last word example we're going to do for this lesson. It's from a VCAR paper. It's from Exam 2, Section B of 2021. So let's have a look. I'm going to read it out. It says, George lives in town G and Maggie lives in town M. The diagram below shows the network of main roads between town G and town M. The vertices G, H, I, J, K, L, M, N, and O represent towns. The edges represent the main roads. The numbers on the edges indicate the distances in kilometres between adjacent towns. What is the shortest distance in kilometres between town G and town M? Okay, so you're supposed to find the shortest distance in kilometres between town G and town M. And this is worth 1 mark. And this is why I've actually picked this question to show you. If we were to do Dijkstra's algorithm, it would take us more than 1 or 2 minutes, which is about the time you get allocated in your exam. So I guess you need to make a decision here. Are you going to use the time-consuming method and make sure you got it right? So can you budget enough time in the rest of your exam? Or are you going to have a go by inspection and sort of just trust your gut that you got it right? If we do, by inspection, if we're going to do it in a minute, that's probably the only way to do it. I don't think I'd be able to draw out Dijkstra's in a minute. So the shortest path ends up being G to O to N to M. And so that's 28 plus 42 plus 16. And so 8 and 2 makes 10. Carry the 1 gives us 86. Okay, so the shortest distance is 86 kilometres. Okay, so worth noting, if you didn't put the units in, you'd probably drop a mark there. And it'd be pretty easy to identify a different path from scratch. Here's our summary. an example of that graph from before with the completed Dijkstra's algorithm. Notice I haven't blacked out the columns, but I've used the numbers there. So just whichever way you feel more comfortable with. And there's some notes if you'd like to put some things in your summary book. All right, up next, we've got matching problems. See you there. Hi, today's lesson is all about matching things, making allocations. When people turn up to play a sport match, I mean, you've probably done this yourself. You shake hands with your opponents and with your teammates when they arrive. So if 5 friends play in a soccer team and when they arrive to train, they all shake hands with one another, how many handshakes have occurred? Can you figure it out? Okay, welcome to matching problems. This part in chapter 8 is sort of separate from the other parts. And from here on out, more or less, we look at like one new concept per lesson. So let's have a look at this one and see if you can do it. In today's lesson, we're looking at 3 main things: bipartite graphs, what are they and what do they look like? Doing weighted bipartite graphs and cost matrices. So they have an associated matrix, talking about their cost. And finally, the Hungarian algorithm, which helps us make allocations. Let's dive in and have a look at what I mean. Okay, so what are bipartite graphs? So bipartite graphs are, graphs where we've sort of got 2 sets of vertices. So here, I've got, some swimmers and the stroke that they're going to do in a medley relay. So all bipartite graphs sort of have these 2 sections. And what you'll notice is that in each group, these vertices are not connected. So the vertices connect from one group to another, but not within that group. So we can have bipartite graphs. We can also have directed bipartite graphs where the connection has a direction. So in this example, we're looking at some friends who want to watch some movies. The directions here indicate which movie has been watched by which person. So you can see that Molly has watched Alien, but the arrow doesn't go the other way because Alien can't watch Molly because it's a film, doesn't watch anything. Okay, one final extra terminology point to look at for bipartite graphs. We've got a complete bipartite graph here. And this definition is similar to looking at the complete graphs from before. If you remember, a complete graph was one where every vertex was connected to every other vertex in that graph by an edge. In this case, that's almost exactly the same. So for a bipartite graph, this node will be connected to every other node in the other group. So this is different because in this graph, not all vertices are connected, because in the bipartite graph, vertices in the same group won't have a connection between them directly. Okay, my example here is I've got some chefs and I've got some dishes or some menu items that they know how to make. Yeah, I think this makes sense because if you think about a restaurant, I think all the chefs in that restaurant probably learn how to make all the dishes. They probably know how to make all the food items, on that menu. So I've got executive chef, kitchen leader, sous chef, and junior chef, and I think they all know how to make French onion soup, bouillabaisse, chicken confit, and croque monsieur. And apologies if I haven't pronounced anything there correctly. Didn't take French in high school. So, at least not for very long. So let's see. Have I missed anything here? A complete bipartite graph has all vertices in the first group connected to all the vertices in the second group. Okay, yep, that seems to check out. I can see the executive chef is connected to all of those. And I think if we went through all the other chefs, that they would be connected to all the other menu items. All right, let's move on. All right, let's look at weighted bipartite graphs and their associated cost matrices. So here we've got a graph. Let's look at that first. We've got Alice, Bob, and Claire, and we've got some exercises, push-ups, star jumps, and squat jumps. So our key takeaway today is that weighted bipartite graphs contain a weight on their edges. This weight can represent cost, time, distance, or some other rate or quantity, anything that makes sense. And so here you can see I've got some weights on each of these. So Alice has a weight of 4 towards push-ups. And so in this example, the weights are representing time taken in minutes to complete this exercise in a exercise circuit. So Alice takes 4 minutes to do her push-ups, and 3 minutes to do her star jumps, and 2 minutes to do her squat jumps. Okay, so if we've got these allocations and we've got these weights, then we can put the weights in a matrix. So here I've got a table matrix, essentially the same thing. And so I put them in there. So you can see I've got Alice's time to do push-ups is 4, 3, and 2, and all the other elements have been put in there as well. The reason we want to do this is because later we're going to run the Hungarian algorithm to find out some best allocations for different sort of activities. All right, onto the Hungarian algorithm. The key takeaway here is that the Hungarian algorithm uses cost matrices to find an optimal allocation of people to tasks. This will give the minimum cost or time for project or allocation. So there's a bunch of steps here as to how to do it, and I'm not going to read through them myself, but you could pause the video and read through them now. We are going to go through step by step, so maybe just come back. Okay, here's the Hungarian algorithm, and I've got the first two steps not grayed out so that we can see them. Step 1 is locate the lowest value in each row, then subtract the value from each element in that row. Step 2 is to find the minimum number of horizontal or vertical lines that cover all the zeros in the table. If it is the same number as the number of people or allocations to be made, then jump to step 7. So in this table, we've got 4 people. And if I want to do this step here, it says locate the lowest value in each row and subtract that value from the element in that row. So here's a table where I think we've done that first step. So if we look at the first row with Andy, the lowest value in there is 4. And I'm going to take away 4 from all of those. So 4 minus 4 would be 0, 10 minus 4 would be 6, 5 minus 4 would be 1, and 11 minus 4 would be 7. And you can see that those are the numbers that are appearing in the row of the next table. So when you do this process, you need to draw several tables and work your way through the problem. You can't do it all with just one table. Okay, so we did that, and we did that for every row. So for Beau's row, the lowest value is 1, and if we take away 1 from all the values in that row, then we should get 5, 7, 0, 1. And then we look at Catherine's row, and the lowest value here is, I think, 7. So if we take 7 away from all of the values in that row, then we're going to get 1, 0, 1, 2. And if we look at Derek's Derek's row up here in the original table, we can see the lowest value is 2. So taking away 2 from all the values in that row gives me 0, 9, 2, 3. Okay, so what you'll notice about doing that process is that we've got a 0 in every row now. And the next step is to find the minimum number of horizontal or vertical lines that cover all the zeros in the table. So to do this step, I have to look for zeros. And, one way to cover all the zeros would be to draw, 4 lines across like this. But that's not allowed because there's a better way of drawing these horizontal or vertical lines. So what I can actually do is draw this line here that covers these 2 zeros. And so I've covered 2 zeros with 1 line, and that's good. You want to try and do stuff like that when you're doing these problems. So here, I can't see any other way to draw lines to cover these 2 zeros in one stroke. I mean, I can't do it. They're in different sort of rows and columns. So I'm just going to draw 2 horizontal lines like that. Okay, once I've done this step, I'm supposed to see, is this the same as the number of people? So there are 4 people, but I've drawn 3 lines. And so I can go to the next step now. Right, so if you'd drawn 4 lines, you'd actually be able to stop at that point. All right, on to steps 3 and 4 of the algorithm. So we've got our table here. Step 3 says to locate the lowest value in each column and subtract that number from every element in that column. Okay, so looking at the columns, setup, filming, color grading, and audio editing. In setup, the lowest value is a 0. And if I take that value away from all the other values in that column, then nothing really happens. 0 minus 0 is 0. 5 minus 0 is 5. 1 minus 0 is 1. And 0 minus 0 is 0. So that column doesn't change. And when the lowest value is a 0, that's going to happen every time. So in filming, I can see there's a 0. So subtracting that won't actually do anything. In color grading, there's a 0. Subtracting that value won't do anything. But in the final column, audio editing, there's a 1. And so I need to subtract that 1 from all the values in that column. So if I do that, I should get, just focusing on this column here, none of these columns change, but this one becomes 6, 0, 1, 2, which is 1 less in all those elements. Okay, so we did that. Okay, just clean the diagram up a bit there. Now that we've subtracted the lowest value within columns, and we can go to step 4, which says find the minimum number of horizontal or vertical lines that cover all the zeros in the table. So again, I try to place horizontal and vertical lines in the best way so that I cover all the zeros. So let's do that. Again, I think I can cover this one here, and that's shaded in. I can cover these 2 zeros with one line, so we'll do that. And then there's only 1 0 left, and now all the zeros are covered, and I've only used 3 lines. So that last part of step 4, it says if the number of lines is the same as the number of people, then I'd go to step 7, but we can't yet. So we've still used 3 lines. We need to be using 4, so we need to go to step 5. Let's do that now. All right, we're getting there. We've got to go on to steps 5 and 6 of the algorithm. So we've got our table there from last time with those rows shaded in. So in step 5, it says locate the smallest value which is not covered by a line. Okay, so we've got our lines that are filled in here. It says subtract that value from all uncovered lines and add the value to the values covered by 2 lines. Okay, that's a little tricky. So let's have a look. First things first, of the uncovered numbers, which one is the lowest? So that's these ones here. They're uncovered. And I think the lowest one is 1. So we're going to maybe circle that so we remember. Okay, there's that lowest value of 1. Now what we're supposed to do is subtract that value from all the other uncovered values. Okay, so we're supposed to subtract 1 from all of these. Okay, but we're also supposed to add that value to the values covered by 2 lines. So which ones are they? They're these ones here. So those ones are going to add 1 to those values. Okay, so if we do that, then we get this table. All right, and you can see we've got lots more zeros now, and these numbers have increased to be 6 and 2. Okay, now we can move on to step 6, which is to redraw those lines. So we want to find the minimum number of horizontal or vertical lines that cover all the zeros in the table. So the same as before, we're just trying to find the best way to place those lines. I think that there's a couple of ways to do it here, but the way I've decided is to first cover this line. So that covers those 2 zeros here. And then I'll use another vertical line to cover these 2 zeros. And then I've got these 2 left. There's no way to cover them with one line, so I have to put 2 more horizontal lines in. Now what you'll notice is that the number of lines that we have is the same as the number of people or the number of allocations to make. So that's sort of what we're going for. So here's step 6. If it is not the same as the number of people, we'd return to step 5. So if you didn't get sort of 4 lines, 4 people, if that didn't match up, then you just repeat this covered, uncovered stage. But they are matching, so we get to move to step 7. Okay, we've reached step 7 of the algorithm, and this is the part where we can say who's going to do what project. So is Andy going to do setup, filming, color grading, or audio editing? What's Bo going to do? What's Catherine going to do? And what's Derek going to do? And so on. And so what we need to do is compare our final table, so that's this one, with our original table, which is the one we started with, and we put it on the slide here. So this is the original table. Okay, the way that we choose who should do what activity is based on the zeros that we've got and their position. So here we can see there are 2 zeros in Andy's row. There are 2 zeros in Bo's row, 1 0 in Catherine's row, and 1 0 in Derek's row. Okay, what this means, so if we focus on Andy, he's got a 0 in setup and a 0 in color grading. And that means that I can sort of choose him to do either one of those. However, I've sort of got to be careful and make sure that I don't stop anyone not having a task. So if you allocate wrong, you might need to start again. What I think is easiest is to start allocating based on the rows that have only 1 0 in them. So we can see that Derek only has 1 0, which means there's only one task he can do optimally. And Catherine has 1 0, and that's one task that she can do optimally. So we can see that this 0 is in the filming column. And so what we can say is that Catherine will be assigned to filming and Derek will be assigned to setup. Okay, now that we've done that, it's actually easier to assign Bo and Andy to a job. And so what we can see if we look carefully here, I'm just going to pull up the highlighter. Okay, so here's my laser pointer. We can see that Bo can do color grading and so can Andy. And Bo can do audio editing and Andy can do setup. So what we want to do here is we can actually make 2 choices, I think. I think we can choose Bo or Andy to do color grading. Oh, wait, no, we can't. We can't do that because Andy, you can see his 0 is in setup. So he can't do setup because we already said that Derek was going to do setup. So what we want to do is assign Andy to the other thing that he can do, and that's color grading. So we're going to assign Andy to be color grading, and that frees Bo up to do audio editing. So let's write that down now. Okay, so we said that Andy would do the color grading, and that means that Bo has to do the audio editing. Okay, we've done the allocation now, which is mostly what we want to do. However, I said that we need to look at the original table. We haven't done that yet. So if we look at, we're going to circle these allocations we've made on the zeros. So we said that Derek was going to do setup. We said that Catherine's going to do filming. We said that Bo's going to do audio, and Andy's going to do color grading. Okay, what we do now is just look at the comparable entries. So the color, Andy's entry here for color grading, that's a 5. That's his initial weight, the time or the cost it takes for Andy to perform that task. So he takes 5 minutes where the others take 1, 8, and 4. So we just match that position on the original table. So Bo will do auto editing for 2, Catherine will take filming for 7, and Derek will take setup for 2. And if we add those weights together, we get the total cost or total time for the project. So Catherine's filming was 7, Derek's setup was 2, Andy's color grading was 5, and Bo's audio was 2. So if we imagine these are hours to complete these tasks, if I add them together now, 7 plus 2 plus 5 plus 2, that gives me 9, 11, 16 hours total. If you allocated the jobs another way, you'd get a different total time. I should be clear here, the one that we've found is the best case scenario. Okay, so we've got to perform the algorithm here all in one step. Let's read the worked example and then I'll summarize what I'm going to do before I do it. We've got Andy, Bo, Catherine, and Derek. They run a production company, so same sort of tasks as before. They can each perform all of the required tasks, setup, filming, color grading, and audio editing. So they can all do those tasks. It's just who can do it the best. We're supposed to use the cost matrix provided and the Hungarian algorithm to find the optimal allocation of tasks and the minimum time to complete the 4 jobs. All times are in minutes. Okay, so to do this, I need to do this process again. The way I think about it in my head is like I go through the rows, and I go through the columns, and then I have to do that weird like covered, uncovered step. And then once I've done all of those, so long as the number of lines I draw match the number of people, then I know I'm done. So I've got 4 tables here. That's my setup for the question. So I'm going to go in this order, 1, 2, 3, 4. And so this is where my final answer will be. Okay, so looking at the first one, I can see that I'm supposed to look at the rows and look at the smallest number and subtract that off. So I can see the smallest number here is 12. So I'm going to subtract 12 from all of these, and I'm going to fill it in down below. So that should give me 6, 0, 7, and 1. Yes, I think I'm happy with that. Yep, that's good. Okay, so now I do the next row. So Bo, the lowest value here is 9, so I'm going to take away 9 from all of those. And you don't have to draw the little 9s in, you can just do it. If you can just do it in your head, that's cool. Just make sure you get it right. So 9 minus 9 is 0, 1, 5, and 16 minus 9 should be 7. Okay, now Catherine's row, I can see the lowest value is 15. So taking away 15 from all of those values is going to give me 0, 1, 2, 1. Derek's row is the last one, and I can see the lowest value in that row is 10. So I'm going to take that away, and that leaves me with 9, 0, 3, and 2. Okay, now I have to try and draw the best allocation of lines, so I'm going to change color and do that. So I'm going to draw a line here, here, and here. So I took 3 lines. That's not the same as the number of people, and so I need to go to the next step, which is to evaluate the columns. So we might use green. I'm going to use green here to look at the columns. And again, I'm just looking for the lowest value in that column and subtracting it off. Remember, if there's a 0 in the column, I subtract 0. And so that effectively does nothing. So here I can see there's a 0 in this column, there's a 0 in this column, and there's a 0 in this column, so they won't change. But the lowest value in color grading column is 1. So I'm going to take away 1 from all of those. Okay, so 7 minus 1 is going to give me, so I'm going to do it for 6, 0, 1, and 2. Okay, I'm going to fill in the rest of the numbers. Okay, so that's done now. I've subtracted that 1 from everything in the color grading column, and now I have to redraw my lines as best as possible. So I'm going to draw the lines like this, and I think that's the best I can do. And again, I've drawn 3 lines, but that's not the same as the number of people there are or the number of allocations. So I need to go to the next step, which is to look at the covered and uncovered values. So I'm going to switch color here to orange. And now I can see the uncovered values. I've got 6, 9. So these are all uncovered. Okay. And so I can see the lowest one there is 1. So I've got to take away 1 from all of those, but I've got to add it to the double covered values. So I take away 1 from all of these, but I add 1 to 5 and 1. Okay, so let's fill in the values now. Okay, so there's the new values where I've added or subtracted 1. And now I'm supposed to draw my lines again. And so I'm going to do that. And this time I think it's going to end up being 4 lines. So let's do it. There's 1. There's 2, 3, and 4. Okay, so I've had to draw 4 lines. And that means that I can stop the algorithm. Now I can make the allocation. So to do that, I'm going to look at the rows with only 1 0 in them. So, and I'm going to box them in red. So I can see Derek has only 1 0 row, which is here. So he'll do filming. Catherine is going to end up doing setup. And then I can see that Andy has an option of doing filming or audio editing, but Derek's already doing the filming. So he's going to do the audio editing, and that leaves Bo with the color grading. Okay, so my allocation here is that Andy will do audio, Bo will do color, Catherine will do setup, and Derek will do filming. Okay, if I want to find the weights or the cost or the time in minutes for this question as to how long that will take, I need to compare to the positions in the original matrix. So they are, so the filming one is down here. So Derek's going to take 10 minutes to film. Catherine is doing setup, and that's 15 minutes in the corresponding position. Color grading, Bo is doing color grading, and his position is here. He takes 10 minutes to do color grading, and Andy is doing audio, and that position is here in the first matrix or table, and that's 13. So they're all the individual times it takes to, for those people to do those tasks, and if we add them up, then I think we get a total of 48 minutes to complete all of them together. So that's the Hungarian algorithm. I've had to go now, and I think it's your turn. That's it for today. That might have been a lot. And when you do this yourself, you've got to draw the tables out. You can't take that shortcut. So you should probably just, draw a few tables out before you get started. We've left the steps here for you to look at if you'd like to copy them into your band reference, as well as some definitions about the terms we looked at today. Up next, we've got precedence tables and activity networks. So I'll see you there. Okay, today's lesson is all about precedence. So do you know which came first, the chicken or the egg? What do you reckon? All right, let's check out activity networks and precedence tables and what they're for. In today's lesson, we've got 3 main points to look at. That's precedence tables, activity networks, sort of how they're connected, and also looking at what dummy activities are and what they mean. Okay, first up, we've got precedence tables. Our key takeaway here is that a precedence table shows all the activities in a project or task. It also contains information on the immediate predecessor of each activity. So what's going on here? If you've got some project that you want to do, sometimes some jobs need to be completed before others. And so in that case, we might like to map that out so we can plan effectively. Part of this is assigning times to those different parts or jobs and figuring out how long the whole project will take. Okay, so we've got this definition here of an immediate predecessor. And so that's an activity that must be completed before another activity can begin. Notice that some activities in a project do not have an immediate predecessor. So activity A doesn't have an immediate predecessor, and that means it's one of the first activities you do in a project. Here we can see that activity B has an immediate predecessor of A, which means you need to finish activity A before you start activity B. And finally here, we've got activity C, and it's got an immediate predecessor of B. So this means we have to do A, then do B, then do C. All right, in this slide, I'm giving an example of a project that we might have. So I'm sort of assuming that some of you out there probably work in a fast food restaurant, or you have a friend that does. And so I've got a list of activities here that you might perform when you're completing an order for a customer. So these activities are here. We've got take order, cook fries, cook burger, salt the fries, assemble the burger, package fries, package the burger, and serve the customer. So there's lots of little mini tasks in there of getting that food to the customer. I've got a few other points to make here about immediate predecessors. They can be required for more than one activity in the precedence table. So sometimes before you can do, say, B and C, you'd need to finish A, or you need to finish A and B before you start D. An activity can have more than one immediate predecessor. So if we look at this table, we can see that H has two immediate predecessors, F and G. So we need to complete packaging the fries and packaging the burger before we can give that to the customer. What I should point out here is this immediate word, because you have to take the order as well before you serve the customer. But that's not, we can see here that A is not here. So why not? It's because it's not an immediate predecessor. There are activities in between taking the order and serving the customer. So understand that the immediate predecessor is related to the activity like just before the one you're about to do. Okay, on to activity networks. And I've got a really simple activity network here. That's this thing. So it's a graph that represents those activities. This is the same table from the start of the lesson, and I've just drawn an activity network here. So this is our precedence table. This is our activity network. Cool. So you might like to look at those two things and see why that picture makes sense for that table. I encourage you to do that and just think a little bit about it. Okay, I've got some stuff here to tell you. So an activity network is a directed graph that contains the information of a precedence table. The activities are represented on the edges, and the vertices remain unlabeled apart from the start and finish. So this is actually different to things we've done in the past. We usually label the vertices, but in this case, we're labeling the edges. Okay, so the last thing to say is the activities without an immediate predecessor are the edges pointing away from the starting vertex. Okay, so what do I mean by that? Here, A doesn't have any immediate predecessors because you have, like, when you start the project, whatever it is, you start at A. Okay, let's move on. All right, here's a worked example for us to try. This one asks us to construct an activity network from the precedence table below. And I think this is actually harder than going the other way. If you've got an activity network and you have to produce the table, I think that's easier than going the other way. The reason is because we're not giving it any structure for this picture. And so this is a bit of like trial and error here involved, that you might need to have a couple of goes at drawing the diagram. Because I wrote this question, I sort of know what it comes out to be. But don't think just if I can get it in one go that you should have been able to as well. So yeah, it's sort of normal to have a few goes at this to get your picture exactly right. Anyway, let's begin and have a go. So I've got all these tasks, and I've got their descriptions here, but that doesn't really matter for drawing the task. So I'm just going to sort of ignore them for now and look at activities and their immediate predecessors. So I can see that A doesn't have any immediate predecessors, and that means it must be at the start. So I'm going to draw in here start, and I've drawn a vertex there. Okay, so then I know that I do activity A straight after the start, and I can see that A is an immediate predecessor for B and for C. Okay, so I think that what's going to happen here is the diagram is going to fork out. So I'm going to draw a vertex. So I've done activity A, and that means I can start activity B, and I can start activity C. And I'll close those off with another vertex. Okay, so now looking at the diagram, I've got, I've drawn these three in. Now I need to draw D, and its immediate predecessor is B. So D needs to happen after B. Close it off with the vertex. And I can see that E needs to happen after C. There's C and E. Now, I've started drawing this in a nice sort of hexagon because I know it's going to come out that way. But you could sort of choose to draw these off in any direction. All right. So here we've done D and E. I need to draw in F and G. So I can see that F, its immediate predecessor is D. Okay. I can also see that G has an immediate predecessor of E, and that H has predecessors both of these. So what sort of needs to happen here is that H needs us to finish F and G. So F comes straight after D, and G comes straight after E, and both of those are the immediate predecessors for H. And that's the last one. So we close off our vertex, and that's the finish. Okay, that's our diagram there. Okay, let's take a look at dummy activities. So our key takeaway today is that activities which share immediate predecessors can make it difficult to draw an activity network. A dummy activity is an edge used to indicate precedence when no real activity is present. So what does this mean? I said before that if you're trying to draw an activity network from a table, that can be challenging. And that can be quite challenging and take several goes to get it right. And sometimes it's not even possible to draw it in such a way that you can connect the activities in a nice way to show the precedence. And in this case, we need the dummy activity. So I want to point out here this dummy activity, that's the dotted orange line, and I encourage you to draw your dummy activities as a dotted line so you can tell them apart. Here we can see that activity C, has two immediate predecessors, A and B. But just the way that the rest of the diagram turns out, there's no way to have A and B pointing into C. So what we do is we have A and B forking off here, and then we need B to be shown to be a immediate predecessor for C. And so we just draw in this dummy activity and label it D. And what that's showing is that, hey, B still needs to be finished before you start activity C. But we also want to be clear that this isn't another activity. It's not some other task that you have to do. It's just showing you the precedence. That's what it's trying to do. Okay, so this last thing that I've got here is that a dummy activity will be drawn from the end of a shared immediate predecessor to the start of the activity with an additional immediate predecessor. What's going on there? So the shared immediate predecessor, what's that? Well, that's B. Okay, both D and C, activities C and D, both require that B is finished before they start. Okay, so that's one way you can spot when you're going to have to draw a dummy activity. Is there a shared immediate predecessor? Okay, also, the dummy activity will be drawn from that immediate predecessor. So notice that the shared one here, B, the dummy activity has started at B. Okay, it's going to point to the start of the activity with an additional immediate predecessor. So notice here that C has two immediate predecessors, has an additional one. And so this is sort of what we look out for in a precedence table to indicate that we have to draw a dummy variable. Have we got an additional immediate predecessor? And is there a shared immediate predecessor? And if so, you draw the dummy activity from the shared to the one that has additional IPs. Okay, let's move on. Okay, here's a worked example. We've got to consider the below activity network and the precedence table to try and fix this activity network. It says we have to sketch a dummy activity on the graph provided to fix the network. Okay, so there should be a dummy activity somewhere here, and we have to draw it in. To do that, we better evaluate this table. So let's have a look. We've got all these different tasks. So we've got take order, toast buns, cook patty, cook fries, assemble burger, package fries, package the burger, and serve the customer. So, okay, that's great. What we want to do when we need to find a dummy activity is to look for a shared immediate predecessor and an activity that has an additional immediate predecessor. So there are two activities here, E and H, that have additional immediate predecessors. Okay, So I found two activities that have those additional IPs, and now I want to look for one of the activities that sort of is a predecessor for more than one activity, and I can see that that's B. So there's the shared immediate predecessor. And so when I draw an activity network, I want to draw it from the shared immediate predecessor to the relevant activity that has two additional immediate predecessors. So in other words, I'm going to draw this from B to E. Okay, so I better label all these so we can see this clearly. So we can see take order was A, toast buns was B, cook patty was C, cook fries was D, assemble is E, package fries is F, package burger is G, and serve customer is H. Okay, so I was supposed to draw that dummy activity from B to E, and so that's going to look like this. Okay, we label that dummy activity D. Okay, and so that seems to work. That's checking out, and I think we can move on. All right, in this example, we've got to draw the activity network from scratch from this precedence table. In this one, I have included a dummy activity, so we need to watch out for that. And we can sort of see it happening here. So there's the shared activity, and D has an additional activity. So I think the dummy is probably going to go from C to D. Okay, let's start drawing. And so we'll put the start in, draw a vertex. And then I can see that A is the only one without any immediate predecessors. So we'll just draw A coming out of the start. And then here I can see A is an immediate predecessor for B and C. So I'm going to draw a fork off here. Okay, and then I can see that D requires C and B finished, and E requires that just C is finished. So I'm actually going to draw this one first, because that's clear to me that E only has one immediate predecessor, and that's C. So I can fill that in. And now I can see that D has immediate predecessors C and B, but it's a little bit hard to draw. I couldn't have drawn B and C into one vertex. That's not really working. And so this is where we need that dummy activity. So I'm going to draw D coming directly out of B, and then connect C to D with that dummy network there. Okay, now the rest is fairly trivial. We can see that F needs to occur as soon as D is finished. So that's going to come out of D. And just sort of looking ahead, I can see that H requires F and G are finished, sort of like we were looking at last time. So I can just finish the diagram like this. So E happens just before G, and H requires F and G, just like that. And so that's the finish. Okay, so I did write this question, so I sort of knew what it was supposed to be like. If I was seeing this for the first time, I might not have been able to do it all in one go or do it that quickly. So make sure that you don't give up if you don't get it right the first time. Okay, I think this worked example is a little bit easier because I find it easier to make the table, the immediate predecessor table, from the activity network. So here I can see that we've got a start, and A and B sort of start at the same time. And so I'm going to put all the activities down, A, B, C, D, E, and F. And A and B don't have any immediate predecessors, so I just put a dash in those columns. Okay, I can see that C happens directly after A, so A is an immediate predecessor of C, and likewise D happens directly after B, so B is the immediate predecessor for D. Okay, a little bit more to think about now that we move on. We can see there's a dummy activity here, but I can see that E requires that C is finished. And so I can see that C is the immediate predecessor for E. And looking at F, now the dummy is pointing in here to F, and so that means that C must be finished before F can start. So I think C is an immediate predecessor for F as well as D. Okay, so we've made the table from the picture, which is probably the easier way to do it. All right, that's it for today. I've left you some notes here on precedence tables and activity networks and dummy activities. There's also some nice diagrams there that you might like to add to your bound reference. All right, up next we've got critical path analysis. So I'll see you there. Hi, today's lesson is about teamwork. And when you work in a team, a phrase you hear sometimes is, we can only go as fast as the slowest member. So I've got a riddle here that's sort of about that. It's a pretty famous riddle. Let's see if you can solve it. I'm going to read it out to you. The Beatles have a show they need to play, but they must cross a bridge to get to the stage. The bridge can only hold a maximum of 2 band members at a time, and it's very dark, so they need a flashlight to cross the bridge. The band members can cross the bridge at different speeds, but the group of 2 crossing at any given time can only go as fast as its slowest member. The band members can cross in the following amount of time. John takes 1 minute, Paul takes 2 minutes, George takes 5 minutes, and Ringo takes 10 minutes. How can you get the band to the stage in 17 minutes total? You should try this riddle yourself. It's classic. Heaps of people have seen it. But there's a link here that shows you the answer if you want to find out. Welcome to the lesson on critical path analysis. In today's lesson, we've got 5 key knowledge points to look at. We've got weighted precedence tables and activity networks. We've got earlier start time, later start time, float time, and critical paths. And all these 5 ideas sort of link together as we develop the ability to do a certain algorithm. So let's have a look. In previous lessons, we looked at the precedence table and we looked at activity networks and how those 2 things are linked. We did this so that we can build up to learning how to find the critical path. So our key takeaway today is that weights added to an activity network usually indicate the estimated time to complete an activity. A project's minimum completion time can be determined by evaluating the weights on the activity network. So what does this mean? This activity network here, this picture, represents some project that we want to finish. It might be a business project. It could be as simple as some examples we've seen before, like serving a customer at a fast food restaurant. These networks allow us to evaluate the optimal way of completing this project. And the next lesson after this one is about trying to make some changes to optimize that sort of project. All right, let's push ahead. So after doing that last question, hopefully it makes sense how we can figure out, the time difference between the start and some activity that we choose. What we want to do is be able to do this for all the activities in the network, and therefore that will let us figure out the finish time. So our key takeaway today for earliest start time is to minimize a project's completion time, each activity should begin at its earliest start time. To find the EST for each activity, we complete a process called forward scanning. Okay, so how do we do forward scanning? There's some steps here, and we're going to do it in the next slide. So our steps are to draw a box with 2 cells at every activity of the network. So we can see that's being done here. And we also need to add additional boxes at the finish vertex. So this finish vertex needs its own double cell box as well. Step 2 says fill in the earliest start time in the left cell of each box. So that's these ones here. So we'll fill in all these boxes first until we get to the finish. Okay, for the EST of an activity with 1 immediate predecessor, add the activity's weight plus the weight of its predecessor. For the EST of an activity with more than 1 immediate predecessor, we add the activity's weight and the greatest weight of all the immediate predecessors. This gives us the largest value. So more on this in the next slide. We'll see it in action. Step 3 says the EST of the finish vertex is the minimum completion of the project. Okay, so here's our worked example. I'm going to run forward scanning here on this network. We're going to see that I can get the EST for all these activities and the finish. Okay, so we start at the start, and that's at a time of 0. So we can start activity A at the 0th minute or the 0th hour. And then activity A, I can see takes 5 hours or minutes, or it takes 5. And that gets me to the start of C in the 5th minute, say. Okay, so the earliest start time for C is 5. And I think because B takes 3 minutes to complete, then the earliest start time for D will be 3. Looking at E, if my earliest start time for C is 5 minutes and it takes 11 minutes to finish C, then I think that the earliest start time for E is 16 minutes. And likewise for F, it takes 12 minutes to finish D, and we can only start it in the 3rd minute, and that gives me a earlier start time of 15 for F. Now I have to make a choice. So, if I'm walking along this way here and this way here, we can see that G requires that both E and F are finished before it can start. Okay, so G has 2 immediate predecessors, E and F. And I think coming from activity E, so 16 plus 7, the earliest we can finish that is going to be 23 minutes. And walking along, coming from F, that's 15 plus 9, which gives me 24 minutes. So we can see here that they don't actually finish at the same time. But because G needs both of them to be finished, it needs to wait until F is done. And that means the earliest start time for G is 24. So I took the highest one in this case. Hopefully that's clear. Okay, now it's easy. G takes 15 minutes to complete, and it can only start the 24th minute. And so adding those two together gives us 39. Okay, so we found the earliest start time for the finish. That's a funny sentence. What that means is the earliest we can get to the finish is the 39th minute. Okay, on to the next part of our algorithm. So this is latest start time. So what does this mean? Let's look at our key takeaway. It says some activities may be able to start later than the earliest start time possible without impacting on the minimum completion time for the project. You might have noticed this sort of like at this pointy end here where two activities meet. And we saw that one was finishing for the other. What that means is that whatever activity was going to finish first can actually wait a little bit to line up with the other one without impacting that final project time. So the process for finding the latest start time, which is LST, is called backward scanning. So let's look at how to do that. I've got some steps here. And the first step to complete, to do backward scanning is to first do forward scanning. So you have to do EST before you can do LST. So step one, I've actually animated in there. So we run all that first. We have to do that whole process before we can start LST. So now, step two is fill in the LST for the finish as the minimum possible completion time. So this is the same as the EST for this finish. What I do here is every time is just fill in the same number here. Okay. If the earliest start time for the finish is 43, then its latest start time is also 43. There's no reason to delay the finish. You know, if we did that, if we didn't do this step, what would that look like? I'd put, say, a 50 in here. So I just, for no reason, wait 7 minutes to finish the project. That doesn't make any sense. Okay, so these two numbers will always be the same in this box here. Okay, so once you've done that, then move on to step three. It says fill in the LST for the preceding activities. For the LST of an activity with one following activity, subtract the duration of the activity from the LST of the following activity. For the LST of an activity with more than one following activity, calculate each possible LST and choose the smallest value. Step four, the LST of the start should be 0. Let's move on and have a look at how to do this. Okay, so we've got our EST finished here for us. This is the same one as we did. And I'm just going to run LST so you can see it in action. So the first step was to put 43 in this box. And then we look at the next activity to work out what's the latest start time of H. Well, the earliest start time of H is 28, and H takes 15 minutes to complete. And I know that 28 plus 15 is 43. So H can't wait. There's no slack time here. We have to put in 28. So to get that, I did 43 minus 15. Moving on now, we've got to make a choice. So what I can see is that, well, H needs to start at 28. And if you remember here, this F, its earliest finish time was going to be 27. And this G, so we had earliest start time of 19 plus 9 was going to give us 28. So what we can actually see here is if we do 28 minus 7, we get 21. And that's the latest start time for F. Here we have some time to wait. So if F starts at 21, then it will finish at 28. And you can see that that doesn't slow down the project at all. Okay, so that's how we got the latest start time for F. Let's do the same thing here. Let's take 28 and take away 9. And that gives me 19. So we can see there's no slack time on G. G needs to start at its earliest start time. Okay, from here on out, we just subtract. We keep working backwards. So we have a latest start time of 21 for F. And if we subtract 11, so do 21 minus 11, then that gets me to 10. Okay, now you can see that there's a slack time here for D of 1 minute, and there's a slack time here for F of 1 minute. You shouldn't think that both of those activities can wait, because if you wait on one of them, then you're actually starting the next one a minute later. So even though we can see two separate activities with a slack time of 1 minute, that's 1 minute for the whole completion time of the project. Okay, so let's keep moving backwards. Let's keep going along this top path. We've got D with a later start time of 10. And looks like B takes 5 minutes to complete. So 10 minus 5 is going to be latest start time of 5 for B. Okay, before I move on to this one here, onto A, I'm going to complete that bottom path as well. So let's see, the latest start time for G is 19, and I'm going to take away 12, which gives me 7. And now the latest start time for E is 7. I'm going to take away 3, which gives me 4. And now I'm sort of ready to think about the latest start time for A. So what we can see is that A is an immediate predecessor for B and C, okay? So A needs to finish before before B can start and before C can start. So basically A needs to be completed so that we don't lose any time on the project. So here we see that C needs to start at its earliest start time. So we can't delay A at all. So we could delay it for B, but because it's an immediate predecessor for both, we have to take the highest value here. So we need to take 4 minus 4 is 0. Hopefully that makes sense. I've now finished LST, and what you notice is that I've got this box here that's 0, 0. That should always happen. Okay, on to float time. Also, you might see the float times called slack time. The key takeaway here is that float time is the difference between the EST and the LST, so the earliest start time and the latest start time. What this means is that if you've got some room to play with in your project, so we saw there was a difference of 1 minute in the previous example, that 1 minute that an activity can wait without slowing down the project is the slack time or the float time. So here we've got this sentence here. So what does it say? The float time is the maximum amount of time an activity can be delayed without impacting the minimum completion time. Hopefully that makes sense. Let's have a look at an example. Okay, here's our worked example, and this looks like the same network as before, and we need to calculate the float time for activity F and H. So I think we can do that. To do this, we need to run LST, at least for these activities. And I just did this before, so let's fill in the numbers. I think it was 18, 16, 15, that was 10, and that was 9. And this was 6, and this was 4, and this was 1, and this was 0. Okay, so they're the numbers we had before. You can see I can sort of do it relatively quickly. And to figure out the float time of any activity, we just have to do the LST minus the EST. That's going to give us the float time. Okay, so, just doing it for some other question, if I wanted to see the float time here at activity D, I'd do 4 minus 4 is 0. So there's no float time. D has to start immediately. If I find it for C, I have to do 6 minus 5, which is 1. So C can wait 1 minute before beginning without slowing down the whole project. So I was asked to find activity F and H, asked to find their slack times or their float times. So here at H, I can see that 15 minus 14 is 1. So there's a float time of 1 minute or 1 day. I think this might have been in days. Regardless, it's 1. And for activity F, I've got a difference of 1 again. So 10 minus 9 gives me 1. Okay, so we did it. Okay, tying it all together, this lesson's namesake is about, it's critical path. So what is the critical path? An activity is critical if it has a float time of 0. So that means it can't wait to start. It has to start immediately without slowing, in order to not slow the project down. Or the EST and LST are the same. This occurs when a delay in the start time of an activity would have an impact on the minimum completion time. The critical path is a sequence of critical activities from start to finish of the project. So there can be multiple critical paths in one activity network. Okay, so I've got an example here of where the critical path is. We can see that I've finished EST and LST, and you need to do that if you're going to find the critical path. The critical path will then be the path where the activities LST and EST are matching. So you just need to see where those numbers are matching, and that will be the critical path. So we can see here, if we just think about it for a moment, B takes 5 minutes and D takes 3 minutes. So we're getting to this finish at the 8th minute along this bottom path. And then along the top path, A takes 4 minutes and C takes 3 minutes. So we're getting there in the 7th minute. So we can see that the top path is faster and it only takes 7 minutes to finish. And that's why BD is the critical path. The project can only be finished when BD is done. That's the critical path. And why is that important? Well, let's push forward and find out. Okay, here's a worked example. We've got to find the critical path of this activity network. Okay, if I'm asked to find the critical path, I know that I need to do EST and LST before I'll be able to determine it. So that's why we looked at each of those before we looked at this one. You can also see I've got a dummy variable in here, and I want to include that or to see how that influences finding the LST and the EST. So let's dive in. We have to start EST, so let's do that. I've got this network here, and I can start activity A at 0. And I'm just going to go forward now and do this, and hopefully you can keep up. So I've got 2 minutes to finish A, so I can start B in the second minute. I can start C in the second minute, and then B is 3 minutes, so it takes 5 minutes until D can start. And then I've got this dummy activity here. And so what that means is that B has to finish before E can finish. So E has 2 immediate predecessors. It has C and B. Okay, so looking at that, well, I can finish C in the 4th minute, and I can finish B in the 5th minute. So E's earliest start time is actually 5 minutes, not 4. Let's keep pushing forward. I think we can find F. So D takes 2 minutes. That lets me start F at the 7th minute. And E takes 3 minutes, so I can start G in the 8th minute. And so now I've got 2 immediate predecessors for H. So G can be finished at the 9th minute, and F can be finished in the 8th minute. So I have to take the larger one of those. So I take 9, and then 1 minute to finish gives me 10 minutes to finish the whole project. Okay, so that's EST done. Now let's do LST. So I'm going to put a 10 straight away in this box, and taking away 1 gives me 9. And then 9 minus 1 gives me 8. So there's some slack time there at F. And 9 minus 1 gives me 8, but no slack time at G. Okay, going backwards again from G, 8 minus 3 will give me 5. And going backwards from F, 8 minus 2 will be 6. Okay, so now I've got some choices to make. I can see that I could finish C by the 4th minute. So there's actually going to be some slack time here. If I do 5 minus 2, I get 3 at C. But now for B, I have to consider both paths. So E needs to start at the 5th minute. Its latest start time is 5, and the latest start time for D is 6. So even though D could let B wait, E can't. And so we need to do this lower value here. 5 minus 3 gives me 2 as the latest start time for B. Okay, now I can see that B needs to start the 2nd minute. So I have to, for activity A, if I want the latest start time, I have to look at the latest start time for C and B. And I can see that, B needs to start immediately. So 2 minus 2 is going to be 0. All right, so I've done LST now. I've done the EST and the LST. Again, the critical path is going to be along where all the numbers are matching. So from the finish, it's going to be along this way. That's because all these ones here have matching numbers. So that's the path that I need to follow. So H, G, E, and then up through the dummy variable along B and A. I could say that the critical path is a series of networks, and it goes A, B, E, G, H. Okay, awesome. So hopefully you can see why that's the critical path, in that if I slow down any of those activities, then the finish time will be affected. There are some activities off the critical path that can be slowed down, or they can wait a little bit, and that won't stop the finish time being 10 minutes. So if you're in this project and you're working on C, D, or F, one of them get to put their feet up for a minute. Okay, in summary, if you want to find the critical path, you've got to do the EST and the LST first. And if you want to find any float time, do the LST minus the EST. So that's a big concept for today. Next lesson, we're looking at crashing, which is if we speed up one of those activities, how much faster does that make the project? And also, if that costs us money, what's the cheapest way to speed up a project? So let's look at that in the next lesson. 2 older siblings looking after 2 younger siblings and a dog. They share the same responsibilities between them each morning. So they've got to walk the dog, feed the dog, walk to the station with their family, cook breakfast, and feed siblings. Which one of these 2 activity networks do you think makes more sense for the family to do? Okay, today's lesson is about crashing. Let's have a look. Today, we're looking at crashing and crashing with cost. Let's just dive in and have a look at what exactly that is. Okay, in crashing, our key takeaway is reducing the time of activities that are part of the critical path can lower the minimum completion time of a project. The process of reducing the completion time is called crashing. Crashing can cause the critical path to change. So here I've got an example for us to see what this looks like. And a project manager is able to reduce the time of activity D by 1 day. Let's see if this changes the minimum completion time. So here I've got a simple network, and you can see that it's almost exactly the same. So I've got 2 here. In this one, D takes 2 days because it's in days. And here, D takes 1 day. So that's the difference. That's the only change we've made. We're going to see what effect that has on the final completion time of the project. I'm going to run LST and EST for both of these. So I'm going to start with the top one because that's the original. So A and B are both going to start at 0. A takes 2 minutes, so C can start at 2. B takes 4 minutes, so D can start at 4. And each of these activities takes 2 minutes. So 2 plus 2 is 4 coming in from this way, and 4 plus 2 is 6 coming in from this way. So the earliest start time for the finish is 6 minutes. I'm going to run LSD just for completion's sake, so let's do that. So 6 minus 2 is going to be 4, and 6 minus 2 is going to be 4. Awesome. And then my latest start time for C is 4 minutes. Take away 2 minutes for A gives me the latest start time for A is 2. And the latest start time for D is 4. Take away 4 gives me the latest start time of 0 for B. So I can see the critical path for this top diagram is running along the bottom. So there it is there. I've highlighted the critical path in the first network. So now D is going to be reduced by 1 minute, and we're going to see if that changes the critical path or if it changes the minimum completion time. So I've got to do all this again for the bottom network. Okay, let's do it again. Earliest start time for A and B is 0. A takes 2 minutes, so C can start at 2 days, and B can start at the 4th day. So then D takes 1 minute, so coming in from this way, it's going to take 5 days. And C takes 2 days, so coming in from this way is going to take 4 days. So our earliest start time is 5 days for the finish. And now running backwards, we can see that this should be 5. 5 take away 2 gives me 3. 5 take away 1 gives me 4. And 0 and 3 take away 2 is going to be 1. So what we can see is that the critical path hasn't changed because I reduced time on the critical path. Here's the critical path on this network, but we can see that the earliest finish time has changed. So the completion time of the project has been reduced by 1 day, and that's because we made an adjustment on that critical path. All right, let's move on. Okay, here's a really similar example. In this case, I've changed A to be reduced by 1 day. So let's read the question. It says, a project manager is able to reduce the time of activity A by 1 day. Calculate the new minimum completion time and critical path. Okay, so just looking at that first diagram, that one's been done for us, and we can see the critical path is still along the bottom. So let's highlight that. What we can see is that actually there's 2 critical paths. So we can see that both of these paths take a total of 5. So 4 plus 1 is 5 and 3 plus 2 is 5. So there's actually 2 critical paths. There's 2 critical paths, and last time we saw I reduced the time on the critical path, and that reduced the minimum completion time of the project. So now let's see what happens when I make this update here of reducing A by 1 day, and let's see what we get. So let's start here, and we've got A and B starting at on the 0th day, and then A takes 1 day, so C can start on the 1st day, and D can start on the 4th day. D takes 1 day to complete, and so coming in this way is 5 days, and C now takes 3 days, and coming in this way is 4 days now. So we can see the earliest finish time for the project is still 5 days. Running backwards now, let's finish it off. This is 5. 5 take 3 is going to be 2. 5 take 1 is going to be 4. 4 take 4 is 0. And 2 take away 1 is 1. Okay, so we can see now the critical path has sort of changed. The critical path is now just along the bottom. And because we had 2 critical paths, as in both of them took an equal amount of time, reducing one of them didn't actually slow down, didn't speed up the project. So we need to actually adjust both, like an activity on both critical paths, in order to reduce the minimum completion time. So hopefully that makes sense. And, because both of them were equally slow, adjusting one of them didn't speed up the project. Let's look at crashing with cost. In real life, projects cost money. It costs money to pay people to do the jobs, might cost money for infrastructure and so on. And if you want a certain job to go faster, if you want to reduce the time of an activity, that's probably going to cost you money. And so that's what this example is about. You're likely to see some questions in your exam about this concept. If you can't run the critical path, if you can't find that yet, you won't really be able to do this. So I encourage you to go back and sort that out before you look at this part here. Okay, our key takeaway today is that reducing an activity's weight or time usually costs money. Evaluating which time reductions are worth purchasing is an important aspect of project management. So we saw before that sometimes changing activity time doesn't actually speed up the project. And so there's no point spending money if we don't speed up the project, right? That's the logic that we've got to use here. So here's an example. It says an activity network for the restaurant Slow Ronald's is shown. In the next slide, we'll reduce the tasks take order, assemble burger, and box fries at a cost. We'll then evaluate which changes are worth making and which ones do not actually improve the time. So there's our example here. We can sort of consider multiple people working at this restaurant. Some people toast buns and cook fries and package fries, and some people cook patties, assemble burgers and package the burger. And there's a take order at the start and a served customer at the end. So if one of these paths along the top sort of is the limiting path or the critical path, then speeding up processes off that critical path might not actually result in a faster serve the customer finish time. So let's dive in and have a look. Okay, here's our example. Ronald is trying to improve his hamburger bar, Slow Ronald's. The current activity network for a burger and fries combo is given below. Activity times are measured in minutes. Ronald will replace his employee at the service desk with a self-serving machine, thereby decreasing activity A by 1 minute for a cost of $80. By staffing more employees on each shift, he can reduce activity F by 2 minutes for $40 and E by 3 minutes for $60. Find the new minimum time for serving the combo and the minimum cost to achieve this. Okay, so it's not necessarily that we want to actually do all of these activities. We might want to do activity like the reduction for activity A. We might want to do it for E, and we might want to do it for F. We might want to do it for some of these, not all of these. So let's have a look and see which ones are going to actually reduce the total time. And if we want to do the minimum cost, we only want to choose those reductions that make a difference. So here we've got the current activity network, and that one's been finished for us, so we can see that one's done. And I think we can identify the critical path there. So let's highlight that now. Okay, looking at this diagram, I'm just going to highlight those boxes that have the same numbers in them. And that means that my critical path must be along the top here. Okay, we've got a new activity network given to us here, and you can see that those times have been changed. So A has been reduced to 1, F has been reduced to 1 as well, and E was 4 and it's been reduced to 1. So those are the changes we've made. And now we're going to go through EST and LST. Let's work out the critical path and let's see what the reduction is. Okay, so I've got to run this process we've been practicing. So I'm just going to try and do that quickly. So A should start at 0, B should start at 1, C should start at 1. B takes 4 minutes, so D can start at 5, the 5th minute. C takes 3 minutes, but there's a dummy path, so we need to check both ways. So we can get to here from AB in 5 minutes, and from AC, we can get there in 4. So E can start at the 5th minute because it needs B and C to be finished. Okay, adding 1 minute gives us 6 minutes to get to G, and 5 plus 7 gives me 12 minutes to get to F. So then I've got two immediate predecessors here, F and G for H. And 6 plus 3 is 9, and 12 plus 1 is 13. Okay, so I need to choose starting H, that's serving the customer, at the 13th minute. And 1 minute to do that gives me 14 minutes to finish that process. Okay, so what I can see is that finish time has been reduced by 3 minutes. What I want you to look at here is that the total reduction in time was more than that. 1, 2, and 3 minutes there make a total of 6 possible minutes to reduce the time by. But that hasn't happened in this activity network. And so some of those must be redundant and not actually helping us finish the minimum completion time. So we don't want to do all of them if we want to find the minimum cost of reducing this time. Okay, so let's finish off. Let's go backwards. So 14 minus 1 is going to be 13. And then 13 minus 1 is going to be 12 here for F. 13 minus 3 is going to give me a later start time of 10 for G. So looks like that path's going along the top for now. Okay, 10 minus 1 is going to give me a later start time of 9 for E. 12 minus 7 is going to give me 5 as a later start time for D. And now I think I've got to think about this dummy network a little bit. So I can see that we've got 9 and 5 as our latest start time. So I need to take the lower one of those so D needs to start at the 5th minute at the latest. So that means that 5 minus 4, I still need to start B at the 1st minute, even though E could wait for that process. Okay, here as well, I've got to finish C. So 9 minus 3 is going to be, I could start this at the 6th minute. And then again, I've got 2 choices for the latest start time of A. I could choose 6 or 1. Again, I want to take the lowest. So B needs A to start at the 0th minute to run this most efficiently. Okay, so let's highlight that critical path. So where do all my numbers match? That's here. And I'm going to highlight that path this way. Okay, so that critical path hasn't changed, and that's okay. So let's evaluate what actual changes made a difference here. Okay, so the things I changed were A, F, and E. So what made a difference? So I think A definitely made a difference. It was on the critical path. So for sure, reducing that contributed to that drop there. And the other one that has changed was F. That was on the critical path. It's been dropped by 2 minutes there. And that's the total 3 minutes that we've lost from the finish on A and F. So A and F are the useful ones. We can see here that changing E didn't actually make a difference. And that cost us $60 to do. That was $60 wasted, I think. So the new minimum time is going to be 14 minutes. And the minimum cost to do this is going to be the cost of those activities that mattered, right? So we don't want to actually change E. There's no point in doing that. We can still reach 14 minutes if E stays the same. And the cost was going to be the $40 to change activity F and the $80 to change activity A. So the minimum cost is going to be $40 plus $80 was going to give us $120. Okay, we did it. Okay, so we looked at crashing, and we looked at crashing with cost, and we looked at a VCAR example of that. What you'll notice is that I can use the algorithm, but I can also if I understand how the algorithm works, I can sort of do some shortcuts to work out some VCAR problems. So make sure you do lots and lots of practice with the algorithm, but also look at some exam type questions so you get some practice of sort of how to do it quickly. All right, I'll see you next time.